Many of the popular ideas in science, like quantum mechanics or the theory of relativity, are well known and often discussed. But in this session, we'll be focusing on concepts that go beyond these mainstream topics, ideas that challenge even seasoned scientists. This isn't going to be about the usual theories you hear in science documentaries. Instead, we'll explore more complex, lesser-known scientific ideas. These are topics that often escape the public eye, but are just as crucial for understanding the deeper workings of the universe. We'll cover ideas that push the boundaries of our understanding and invite us to think in entirely new ways. This journey will be thought-provoking, perhaps even mind-bending, but we'll take it step by step, delving into these intricate ideas and exploring the mysteries they present. Vacuum catastrophe. Imagine a vacuum, empty space, devoid of matter, a pure nothingness. In our everyday experience, the idea of nothing seems simple. But in the realm of physics, particularly quantum mechanics, nothing is far from simple. In fact, what we think of as empty space is buzzing with activity. This is where the vacuum catastrophe comes into play, a conundrum that continues to perplex scientists. In quantum field theory, the vacuum isn't truly empty. It's filled with what we call vacuum energy, a kind of residual energy that fluctuates at a microscopic level. Imagine a calm lake where beneath the surface there's constant movement, ripples, bubbles, and swirls that we can't see. In the vacuum of space, this energy is always shifting, causing what we call virtual particles to pop in and out of existence. These particles appear for a fraction of a second and then vanish, contributing to what we understand as vacuum energy. The vacuum catastrophe arises when we attempt to quantify just how much energy exists in this empty space. Based on quantum mechanics, we can calculate the vacuum energy density, and the result is staggering. So high that if it were correct, the universe as we know it shouldn't exist. The calculation suggests that the vacuum energy is 120 orders of magnitude larger than what we observe in reality. To put this in perspective, that's a number with 120 zeros after it, an incomprehensible difference. It's the largest discrepancy between theory and observation in all of physics. To understand this better, let's use an analogy. Imagine you're an architect tasked with designing a small bridge over a stream. You calculate the weight the bridge can support based on materials and construction. Now imagine you're told the actual weight capacity of the bridge is equal to the weight of the entire Earth. A number so absurd that it makes you question whether your initial calculations had any grounding in reality. That's the gap scientists face with the vacuum catastrophe. So, how did we end up with such a huge mismatch? The vacuum catastrophe ties directly into the cosmological constant problem, which originates from Einstein's theory of general relativity. The cosmological constant was introduced by Einstein to account for a static universe, though he later called it his biggest blunder after discovering the universe was expanding. However, the constant made a surprising return when we began studying dark energy, the mysterious force that's driving the accelerated expansion of the universe. The vacuum energy should, in theory, be related to the cosmological constant. But when we compare the tiny value of the cosmological constant observed in reality to the huge value of vacuum energy calculated from quantum mechanics, we are left scratching our heads. Scientists have been searching for answers for decades. Some propose that there's something fundamental we're missing in our understanding of quantum mechanics or general relativity. Others suggest that the answer could lie in a yet-to-be-discovered theory that unites quantum mechanics with gravity, such as string theory or quantum gravity. But so far, no one has found a solution that satisfactorily closes this 120 order of magnitude gap. This isn't just a theoretical problem. It's one that strikes at the heart of how we understand the universe. If vacuum energy really was as enormous as our calculations suggest, the fabric of space itself should be tearing apart at every moment. Galaxies, stars, and planets wouldn't be able to exist, let alone life itself. The fact that we observe a relatively calm universe means that either we've made a colossal error in our calculations, or that there's a piece of the cosmic puzzle we haven't yet uncovered. In the world of physics, the vacuum catastrophe is one of the most glaring reminders that despite all we've learned about the universe, many mysteries remain. It's a paradox where theory and reality are wildly out of sync, urging us to dig deeper into the fundamental nature of the cosmos and pushing the boundaries of our understanding. Bohmian mechanics. Bohmian mechanics is one of those ideas that takes us back to a fundamental question about the universe. How do things move, and why do they move the way they do? When we think about the microscopic world, the world of atoms and subatomic particles, it's governed by quantum mechanics, which is filled with uncertainties, probabilities, and wave functions that seem completely counterintuitive to our everyday experiences. But Bohmian mechanics offers an alternative interpretation, one that paints a more deterministic picture of the quantum world. Imagine you're trying to describe the motion of a car traveling along a winding road. In classical physics, you can easily calculate its position, speed, and direction at any given moment. But in standard quantum mechanics, the car isn't on a specific part of the road at all. It exists as a wave of probabilities. It could be anywhere on the road, and we only know its exact position when we measure it. This is the essence of the famous Copenhagen interpretation of quantum mechanics, which emphasizes the inherent uncertainty in a particle's position until it's observed. Now, Bohmian mechanics takes a radically different view. It proposes that the car, like particles in the quantum world, always has a well-defined position and velocity even if we don't observe it. Instead of just being a fuzzy probability wave, Bohmian mechanics suggests that particles follow a clear, well-defined path. So in this interpretation, the car is always on the road, following a specific route. But there's a twist. It's being guided by something called the pilot wave. The idea of the pilot wave is central to Bohmian mechanics. You can think of it like an invisible GPS system for particles. This wave influences the trajectory of every particle, determining where it will go, and it operates according to the wave function that standard quantum mechanics uses to describe probability. So, while particles are still subject to quantum behavior, they aren't merely floating in uncertainty. They have a hidden guide that directs their motion. Let's break it down with an analogy. Imagine you're floating down a river in a canoe. The river's current, representing the pilot wave, is guiding your movement. Even though you may not see all the twists and turns ahead, the current knows exactly where it's taking you. You're not drifting aimlessly. The river is controlling your path. In Bohmian mechanics, the particles of the quantum world are like your canoe, and the pilot wave is the river that guides them, ensuring they follow a deterministic path. This deterministic nature of Bohmian mechanics stands in contrast to the randomness inherent in the Copenhagen interpretation. In traditional quantum mechanics, there's an intrinsic unpredictability. Particles don't have a defined position or momentum until measured. Bohmian mechanics rejects this randomness and insists that the universe operates in a completely predictable way. If we knew all the variables, we could, in theory, predict exactly where every particle would be at any moment, even in the quantum realm. However, Bohmian mechanics is not without its critics. One of the main points of contention is that it introduces this hidden pilot wave, which we can't directly observe. It feels almost like adding an extra layer to the universe to explain something that quantum mechanics already addresses, albeit with uncertainty. Some physicists argue that the elegance of quantum mechanics lies in its simplicity, and adding a guiding wave complicates things unnecessarily. On the other hand, supporters of Bohmian mechanics argue that it provides a clearer, more intuitive understanding of the quantum world. The idea that particles follow definite paths is much easier to grasp than the abstract probability waves that exist in the Copenhagen interpretation. Plus, Bohmian mechanics offers an answer to the so-called measurement problem, the question of how and why observation causes particles to adopt a specific state. In Bohmian mechanics, there's no mystery here. Particles always have a state, whether we observe them or not. This interpretation of quantum mechanics is named after the physicist David Bohm, who developed it in the 1950s. His work challenged the dominant views of quantum mechanics at the time, and opened the door for new ways of thinking about the quantum world. Although Bohmian mechanics remains a minority view in the physics community, it has continued to attract attention and research, particularly from those who are uncomfortable with the inherent randomness of standard quantum theory. Ultimately, Bohmian mechanics provides a thought-provoking alternative to our understanding of the quantum universe. It reminds us that even in the realm of the very small, where uncertainty seems to reign supreme, there may be hidden layers of reality guiding everything with precision and order. Whether or not it's the true description of quantum mechanics, Bohmian mechanics offers a deterministic lens through which we can re-examine the chaotic, unpredictable nature of the quantum world. Black hole information paradox. The black hole information paradox is one of the most perplexing puzzles in modern theoretical physics. To truly grasp its strangeness, imagine this. You have a book in your hands, filled with all kinds of information, stories, facts, diagrams. Now picture tossing that book into a black hole. The question is, what happens to the information inside? Does it simply vanish, or is it somehow preserved? This seemingly simple question has confounded physicists for decades and strikes at the very heart of our understanding of how the universe works. Black holes are already strange enough. They form when a massive star collapses under its own gravity, creating a region of space so dense that not even light can escape its pull. Once something crosses the boundary of a black hole, known as the event horizon, it's lost forever, or so it seems. From the outside, black holes appear to be black voids, with no clues about what's going on inside them. But according to the laws of quantum mechanics, information can't just disappear. It's like throwing a letter into a fire. Sure, the paper may burn, but the information in the letter should technically be preserved in some form, even if it's scattered in the ashes. This is where the paradox begins. The central problem stems from two fundamental principles of physics. On one hand, Einstein's theory of general relativity tells us that anything crossing the event horizon of a black hole is swallowed up and can never escape. But on the other hand, quantum mechanics insists that information about physical systems can't simply disappear. In physics, information refers to the specific details about particles, their position, momentum, energy, etc. If this information is lost forever in a black hole, it violates the fundamental laws of quantum mechanics. And here lies the paradox. Black holes seem to destroy information, but the laws of physics say that's impossible. To understand this better, let's return to our analogy of the book. Imagine that book represents the information about a physical system, its atoms, energy, and configuration. When it's thrown into the black hole, classical physics based on general relativity says the book will disappear into the singularity, and any information about it will be lost to the outside universe. But in quantum physics, information is indestructible. It's like throwing the book into a locked vault rather than incinerating it. It's still there, just hidden. The black hole, in this sense, is both the fire and the vault, which is why it creates such a paradox. Stephen Hawking made this paradox even more famous in the 1970s when he discovered something unexpected. Black holes are not completely black. They emit what is now called Hawking radiation. This radiation slowly leaks energy away from the black hole over time. Eventually, this leads to the black hole evaporating entirely. But here's the catch. Hawking's calculations suggested that the radiation emitted by the black hole is completely random. It contains no information about what fell into the black hole. So, if a black hole completely evaporates, what happens to all the information about everything it swallowed? Is it gone forever? This presents a serious problem because if information is truly lost in this process, it would undermine one of the most fundamental principles of quantum theory, the principle of unitarity, which essentially guarantees that information is preserved in the evolution of physical systems. If black holes could destroy information, it would force physicists to rewrite the rules of quantum mechanics, which would have profound consequences for our understanding of the universe. Many solutions have been proposed over the years, but none have definitively resolved the paradox. One idea is that the information is somehow encoded in the Hawking radiation itself, but in an extremely subtle way. This would mean that as the black hole evaporates, the information leaks out slowly, but we just don't have the tools to detect it yet. Another theory proposed by Leonard Susskind and others is that the information isn't lost, but is smeared across the event horizon of the black hole, an idea known as the holographic principle. In this view, all the information that falls into a black hole is stored on its surface, much like a hologram, while the interior remains empty. One of the more extreme ideas is that black holes don't destroy information because they don't truly evaporate. Instead, they might leave behind some remnant, a leftover object after the black hole evaporates, where the information is somehow stored. Others have suggested that the paradox points to a need for a more fundamental theory of gravity that integrates quantum mechanics, a theory of quantum gravity. In this scenario, the paradox arises because we don't yet fully understand the true nature of space and time. Ultimately, the black hole information paradox reveals that we are still missing crucial pieces in the puzzle of how the universe works. It's a riddle that sits at the intersection of quantum mechanics, relativity, and cosmology, our best theories for explaining the fabric of reality. Solving it may lead to a deeper understanding of the universe, or perhaps even a new theory of physics that could revolutionize everything we know about space, time, and information. For now, it remains one of the most tantalizing unsolved mysteries in science. A paradox that challenges the very boundaries of human understanding. Causal set theory. The concept of causal sets presents an entirely different way of looking at the fabric of reality, one that doesn't treat space and time as smooth and continuous, but rather as a series of discrete elements, much like the individual pixels on a screen. Just as a digital image is composed of tiny dots, causal sets suggest that space-time itself might be made up of indivisible building blocks, or atoms, of space-time. This idea fundamentally challenges the smooth, flowing nature of space and time that we've been accustomed to, especially since Einstein's theory of relativity. To understand the idea, imagine a world made of tiny, unobservable pixels. If you zoom in far enough on what appears to be a smooth surface, you'd see that it's actually composed of individual points, each distinct from the others. In the same way, causal set theory argues that the universe at its most fundamental level is not continuous, but granular. These discrete elements are not just scattered randomly. They're linked in a web of cause and effect, meaning that each atom of space-time only exists in relation to others. It's the interaction between these elements that gives rise to the structure of the universe. Now, this might sound abstract, so let's break it down using a familiar analogy. Imagine you're building a city. Each building in the city is like an individual space-time atom. These buildings don't just exist in isolation. They're connected by roads, roots of cause and effect. In causal set theory, these roads represent how one event can lead to another, how one moment can influence the next. It's a bit like how one domino falling can knock down the next in a sequence. Except here the dominoes are moments in time and points in space. The theory posits that the continuum we observe, time smoothly flowing from moment to moment and space stretching out endlessly in all directions, is really just an illusion. Much like how a moving picture in a movie is really just a sequence of still images played quickly one after another. In reality, according to causal set theory, the universe is built out of these tiny, discrete atoms of space-time that form a vast causal network. One of the most intriguing aspects of causal sets is how it challenges our intuition about scale. For example, Einstein's general theory of relativity works incredibly well for large-scale phenomena, like predicting the motion of planets and galaxies. It treats space-time as a smooth, continuous fabric that bends and warps in the presence of massive objects like stars and black holes. But this smoothness may only hold up at macroscopic scales. Just like the surface of a pond appears smooth from a distance, it becomes grainy if you zoom in close enough to see the individual water molecules. Space-time itself may be composed of fundamental grains at the smallest scales close to the Planck length, which is around 10 circumflex 35 meters, an unimaginably tiny distance. Causal sets suggest that at this microscopic scale, space-time behaves very differently. Instead of being a smooth, curved surface as envisioned by Einstein, it becomes a network of discrete points connected by causal relationships. And much like a pixelated image that looks sharp from a distance but reveals its pixelated nature up close, the universe might appear continuous on the large scale, but reveals its granular structure when viewed from the perspective of quantum gravity. This brings us to one of the major motivations behind causal set theory, the search for a theory of quantum gravity. One of the biggest challenges in modern physics is finding a way to reconcile general relativity, which describes gravity on large scales, with quantum mechanics, which describes the behavior of particles on the smallest scales. These two frameworks have been incredibly successful in their respective domains, but are notoriously difficult to combine. Causal set theory offers a potential path forward by suggesting that space-time itself is quantum in nature, composed of discrete elements. There are other profound implications as well. For instance, in a universe described by causal sets, the flow of time is fundamental. Unlike in some interpretations of physics where time is viewed as an illusion or a secondary effect of more fundamental processes, in causal set theory, time is real and absolute. Each atom of space-time follows from another, building up the universe event by event, moment by moment, just like how one brick is laid on top of another to build a wall. This could offer new insights into the nature of time itself and the deep question of why time seems to flow in only one direction, from the past to the future. Moreover, the idea that space-time is composed of discrete units could solve some of the most perplexing issues in modern physics. For instance, when we try to use general relativity to describe what happens inside a black hole or at the very beginning of the universe during the Big Bang, we run into infinities, mathematical singularities where the equations break down. But in causal set theory, these infinities may be avoided because space-time isn't infinitely divisible. Just like there's a limit to how closely you can zoom in on a digital image before you start seeing the individual pixels, there's a limit to how closely you can examine space-time in causal set theory. In the grand scheme of things, causal set theory is still very much in the realm of theoretical physics, and it has yet to be tested by experiments. However, it offers a tantalizing glimpse of a future where the mysteries of quantum gravity and the true nature of space-time could be unlocked. By thinking of the universe not as a smooth, continuous expanse, but as a web of discrete, interwoven moments, causal set theory provides a new perspective on the structure of reality itself, a perspective that challenges our most fundamental assumptions about space, time, and causality. Riemann hypothesis. The Riemann hypothesis is often referred to as one of the greatest unsolved problems in mathematics. It lies at the heart of number theory, a branch of mathematics that deals with the properties of numbers. particularly prime numbers. Prime numbers, those numbers that are only divisible by 1 on themselves, are fundamental building blocks in mathematics. The Riemann hypothesis, proposed by the German mathematician Bernhard Riemann in 1859, attempts to unlock the mystery of how these prime numbers are distributed along the number line. At first glance, the problem of prime number distribution seems deceptively simple. After all, primes are just numbers like 2, 3, 5, 7, 11, and so on. But as you move further along the number line, prime numbers become less frequent, appearing seemingly at random. What the Riemann hypothesis suggests is that there is an underlying pattern to this randomness, a hidden rhythm that governs the appearance of primes. To understand this, we need to step into the world of complex numbers. Complex numbers are an extension of the real numbers we're familiar with, but they include an imaginary component, often denoted as I, where I2 minus 1. Riemann's genius lay in the insight that prime numbers could be studied not just through real numbers, but through the complex plane. Specifically, he examined something called the zeta function, a mathematical tool that encodes information about prime numbers. The Riemann zeta function, denoted by the symbol, is an infinite series, a sum of terms that goes on forever. Here, S is a complex number, and this sum converges, meaning it produces a finite value. For certain values of S, Riemann's remarkable insight was that the behavior of this zeta function holds deep clues about the distribution of prime numbers. In particular, the function has special points called zeros, where its value is exactly 0. The Riemann hypothesis is concerned with the location of these zeros. The hypothesis itself is simple to state. All non-trivial zeros of the zeta function have a real part equal to 1/2. That's it. But this simple statement has profound implications for the distribution of prime numbers. If true, it would mean that prime numbers aren't distributed randomly along the number line, but follow a subtle and predictable pattern. In other words, prime numbers have an order to their chaos. To illustrate this with a metaphor, imagine walking along a long, winding beach. As you walk, you pick up seashells, which represent the prime numbers. At first, the seashells seem to be scattered randomly with no discernible pattern. But as you continue walking, you start to notice that although they appear irregularly spaced, there's a hidden order to how they're distributed along the shore. The Riemann hypothesis is like a map that, if proven, would reveal the exact spacing of these seashells, showing that what appears random on the surface is actually governed by a deeper mathematical law. So, why is the Riemann hypothesis such a big deal? For one, prime numbers are the building blocks of all integers, and understanding their distribution could revolutionize many fields of mathematics. But beyond pure number theory, prime numbers play a crucial role in cryptography, the science of encoding and securing information. Modern encryption algorithms, such as those used to secure online transactions, rely on the difficulty of factoring large numbers into their prime components. If we could better understand the distribution of primes, it could have significant implications for the security of digital communications. Despite the importance of the Riemann hypothesis, it remains unproven. Mathematicians have verified its truth for the first several billion non-trivial zeros of the zeta function, but a general proof remains elusive. Some of the greatest minds in mathematics have attempted to crack the problem, but it has resisted all efforts so far. In fact, the Riemann hypothesis is one of the 7 Millennium Prize problems identified by the Clay Mathematics Institute, with a reward of $1 million for anyone who can provide a proof or disproof. The difficulty of the Riemann hypothesis doesn't stem from its complexity, but from its deep connection to many different areas of mathematics. It intertwines with fields like algebra, geometry, and even physics. Some researchers have speculated that the Riemann hypothesis might be connected to quantum mechanics, the branch of physics that describes the behavior of particles on the smallest scales. In this view, the zeta function and its zeros could be linked to the energy levels of quantum systems. This idea remains speculative, but it underscores the interdisciplinary nature of the problem. In summary, the Riemann hypothesis is a profound and tantalizing mystery. It suggests that the seemingly random distribution of prime numbers follows a hidden pattern, one that mathematicians have been chasing for over a century. Proving it would not only solve a long-standing puzzle, but also unlock new insights into the fundamental nature of numbers, with far-reaching consequences for both mathematics and the real world. And yet, despite the simplicity of its statement, the Riemann hypothesis remains one of the most elusive and challenging problems in all of science, standing as a testament to the complexity and beauty of mathematics. Non-cumulative geometry. Non-commutative geometry is one of those concepts that might sound intimidating at first, but it reveals a fascinating aspect of how the universe might be structured on the deepest levels. To break it down, let's start with something simple: commutative operations. When you commute something, like in math, it means the order doesn't matter. For example, in basic arithmetic, 2-3 is the same as 3-2, and 4-5 is the same as 5-4. This symmetry, where the order of operations doesn't affect the result, is something we're very familiar with in our everyday experiences. But what happens if we dive into areas where this simple rule doesn't hold up? That's where non-commutative geometry comes in. In this framework, the order of operations does matter, and that slight change opens up an entirely new way of looking at space, time, and the structure of the universe itself. To use an analogy, think of a deck of cards. When you shuffle the deck, the order of the cards changes, and depending on the specific sequence, you might get a winning hand or not. The outcome is sensitive to the order, just like non-commutative geometry. The universe, on some scales, could behave more like that shuffled deck of cards, where the sequence of interactions changes the overall result. This is different from the calm, predictable world of commutative operations, where the order doesn't matter. But why does non-commutative geometry matter in physics and mathematics? The answer comes from quantum mechanics and the strange behavior of particles on very small scales. In classical physics, we can measure the position and velocity of an object simultaneously without any issue. But in quantum physics, things get weird. There's something called the Heisenberg uncertainty principle, which says you can't know both the position and momentum of a particle at the same time with perfect accuracy. This is because at the quantum level, the act of measuring one property disturbs the other. This inherent uncertainty implies that space and time at the smallest scales aren't smooth and continuous, but rather have a more complex, fuzzy structure. Non-commutative geometry provides a mathematical framework to describe this fuzziness. It allows us to model spaces where the position and momentum of particles don't commute. That is, measuring one affects the other in a fundamental way. In this sense, non-commutative geometry is an attempt to describe a quantum version of space and time. To visualize this, think of a piece of graph paper. In normal commutative geometry, you can measure the position of a point on the paper by moving along the x-axis and y-axis independently. The order in which you measure doesn't matter. You can go left first, and then up, or up first, and then left, and you'll end up at the same point. But in non-commutative geometry, imagine that the paper itself is somehow distorted or blurred, in such a way that the order does matter. If you go left first, the point you end up at won't be the same as if you had gone up first. The space itself has become non-commutative. Alain Connes, a French mathematician, is one of the pioneers of this field. His work in non-commutative geometry has brought new perspectives to both mathematics and theoretical physics. One of the most exciting applications of non-commutative geometry is in attempts to unify quantum mechanics and general relativity. As you may know, general relativity describes the universe on large scales, planets, stars, galaxies, while quantum mechanics governs the behavior of particles on the tiniest scales. These two theories are incredibly successful in their respective domains, but are fundamentally incompatible with each other. Non-commutative geometry offers a potential bridge between these two worlds. In fact, some theorists believe that non-commutative geometry might be key to developing a theory of quantum gravity, which would describe how gravity works on the quantum level. In such a theory, space and time wouldn't be smooth and continuous as described by classical physics, but instead would be granular, with a non-commutative structure on the smallest scales. This could help explain phenomena like black holes and the Big Bang, where both quantum effects and gravitational forces are incredibly strong. Another area where non-commutative geometry has found application is in string theory, a theoretical framework that aims to describe all fundamental forces and particles in the universe as vibrations of tiny strings. In some versions of string theory, space-time itself is non-commutative, meaning that the positions of strings don't commute in the usual way. This leads to fascinating new possibilities for how the universe is structured on the smallest scales. To make this even more relatable, think about how we deal with everyday objects. In our macroscopic world, if you want to pick up a cup of coffee, the order in which you move your hand and fingers doesn't matter too much. You'll still end up grabbing the cup. But in the world of non-commutative geometry, the sequence of events, or the way objects relate to each other, becomes crucial. It's as if reality itself has an internal shuffle, where the order of actions plays a fundamental role in determining the outcome. In summary, non-commutative geometry is a powerful tool that allows mathematicians and physicists to explore spaces where the usual rules of geometry no longer apply. It offers a framework for understanding quantum uncertainty, the behavior of particles, and possibly even the fabric of space-time itself. While it's still a developing field, Its potential to unlock new insights about the nature of the universe is immense. Whether it will one day provide the key to solving the mysteries of quantum gravity or offer a deeper understanding of the cosmos remains to be seen. But the journey into this non-commutative realm is already changing how we think about the very structure of reality. Twistor theory. Twistor theory is one of the most intriguing ideas in modern theoretical physics, offering a completely fresh way to think about the fabric of reality. Developed by the British mathematician and physicist Roger Penrose in the 1960s, Twistor theory aims to unify two of the most important but seemingly incompatible concepts in physics: general relativity and quantum mechanics. It's a mathematical framework that challenges our conventional understanding of space-time, using light and geometry in ways that, while abstract, offer a potential bridge between the very large and the very small. To make sense of Twistor theory, let's start with a simple analogy. Imagine you're navigating a city and the streets represent different possible pathways you can take. In traditional physics, we think of the city as a map, where every location is a point with precise coordinates, like latitude and longitude. You know exactly where you are at any given moment. And moving from one point to another is as straightforward as drawing a line between them. This is much like how general relativity views space-time, a smooth, continuous structure that can be bent and curved by massive objects like stars or planets. Now, Twistor theory invites us to think about this city in a completely different way. Instead of focusing on your exact position at every moment, imagine you're only interested in the paths you can take, specifically the paths that light would travel. Light doesn't stop and start like a car moving through traffic. It flows along trajectories called null lines, at the fastest possible speed, unaffected by anything in its way. In Twistor theory, these light paths, or null geodesics, are the fundamental elements of the universe, not the points on a map. The city's layout is determined not by fixed locations, but by the interconnections between different light paths. To put it another way, instead of focusing on individual points in space-time, like where you are standing, Twistor theory focuses on how different events are connected by light. This perspective reshapes the way we think about reality, emphasizing the relationships between events rather than the events themselves. So, why is this radical idea important? The answer lies in the long-standing problem of how to reconcile general relativity, which describes the behavior of large objects like stars and galaxies, with quantum mechanics, which governs the tiny world of subatomic particles. General relativity treats space-time as a smooth continuum, while quantum mechanics suggests that at extremely small scales, space-time might not be smooth at all. It might be made of discrete, granular bits. These two views clash, particularly in extreme environments like the center of a black hole or the moment of the Big Bang. Twistor theory offers a potential resolution by sidestepping some of these conflicts. Instead of trying to blend smooth and discrete models of space-time, it proposes a completely new framework, one that operates at the level of light rays and null geodesics. These light-based connections may serve as the common ground between the two seemingly incompatible theories, giving physicists a way to talk about space-time that works in both the macroscopic and microscopic realms. Let's dive a bit deeper into the mathematical core of Twistor theory, though we'll keep it approachable. In classical physics, events in space-time are described using 4 coordinates: 3 for space, like length, width, and height, and 1 for time. These coordinates help us pinpoint the location of objects and their movement through time. But in Twistor theory, instead of 4 coordinates, events are described using twistors, which encode information about the direction and speed of light rays. In a way, twistors collapse some of the complexity of space-time into a simpler, more elegant description, one based on light rather than fixed positions. This brings us to the heart of what makes Twistor theory so revolutionary. In Einstein's general relativity, space-time is a kind of stage where matter and energy move around, interacting with each other through the force of gravity. In quantum mechanics, space-time becomes fuzzy and probabilistic, filled with uncertainties about where particles are and how they behave. Twistor theory, however, removes the stage altogether. It redefines the very concept of space-time, suggesting that the universe's underlying structure is based on light's geometry and its interactions. Another area where Twistor theory has made a significant impact is in simplifying certain complex calculations in quantum field theory. Quantum field theory describes how particles interact through fundamental forces, like electromagnetism and the strong nuclear force. These calculations are notoriously difficult, but Twistor theory has provided shortcuts that simplify some of the math, especially when dealing with high-energy particles. This practical application of Twistor theory has reignited interest in its potential, not just as a theoretical tool, but as something that could help physicists better understand particle interactions. One way to visualize Twistor theory is to imagine you're a surfer riding a wave. Traditional physics would describe your movement by plotting your position at every moment on the ocean's surface. Twistor theory, on the other hand, isn't concerned with your exact position at any given time. It's more interested in the trajectory of your ride, the continuous motion through which you experience the ocean. The wave itself, much like light, defines the relationships between you and the ocean, giving rise to a new way of understanding your journey. In this metaphor, Twistor theory looks not at static points in space, but at the dynamic flow of energy and motion defined by light. In conclusion, Twistor theory is an elegant and innovative framework that challenges our conventional understanding of space-time. By focusing on light and its paths rather than fixed points in space and time, it offers a potential bridge between the macroscopic world of general relativity and the microscopic world of quantum mechanics. Though it remains a developing field, the beauty of Twistor theory lies in its simplicity and its ability to reshape how we think about the universe at the most fundamental level. It may hold the key to answering some of the deepest questions in physics, from the nature of black holes to the origins of space-time itself. Fractional dimension. Fractional dimensions, also known as fractal dimensions, challenge the intuitive way we think about space. We usually conceive dimensions in whole numbers. A line is one-dimensional, a plane is two-dimensional, and a cube is three-dimensional. But nature, in all its complexity, often defies such straightforward categorization. In the 20th century, mathematicians like Benoit Mandelbrot introduced the idea of fractal dimensions to better describe natural phenomena that don't fit neatly into integer-based dimensions. Fractal dimensions are particularly useful when dealing with objects that are self-similar and exhibit intricate, repeating patterns no matter how much you zoom in on them. To understand fractional dimensions, let's first consider something familiar: a simple line, a square, and a cube. A line is one-dimensional because it has only length. A square is two-dimensional because it has both length and width. A cube, being three-dimensional, adds height to the mix. These are examples of integer dimensions. But what about something that is between these dimensions? Something that is more than a line, but not quite a plane. Enter the concept of a fractal, which can exist in dimensions that are not whole numbers. Take the famous example of the Koch snowflake, a shape that begins as a simple triangle. By repeatedly adding smaller triangles to each side, the snowflake becomes more intricate with each iteration. Though it's technically a two-dimensional shape, its intricate detail, no matter how closely you zoom in, suggests it occupies more than 2 dimensions, but not quite 3. The Koch snowflake has a fractal dimension of about 1.26. It's more than a line, but not quite a plane, and its dimension reflects that. You might wonder how something can have a dimension of 1.26, or any non-integer number, for that matter. The key lies in how these objects fill space. A one-dimensional line is straightforward. It stretches across a single axis. A two-dimensional square covers an area, while a three-dimensional cube occupies a volume. But a fractal like the Koch snowflake doesn't fit neatly into these categories. It fills space in a way that's more than one-dimensional, but doesn't fully reach two-dimensional coverage. A fractal dimension is a measure of how completely a shape fills space as you zoom in on it. This concept finds real-world application in numerous natural systems. Consider the structure of coastlines. From afar, a coastline may appear as a simple, jagged line. But as you zoom in, you'll notice more and more complexity. Tiny bays, inlets, and rocky outcrops that reveal new details with every magnification. Coastlines, like fractals, appear self-similar at different scales. Their fractal dimension is not an integer. Instead, it's something between 1 and 2, because they behave like a curve, but have enough intricacies to fill more space than a simple line would. Another fascinating example can be found in the branching patterns of trees. A tree doesn't just stop at its trunk. Branches split into smaller branches, which split into twigs, and so on. This pattern repeats in a way that suggests the tree occupies a space somewhere between 2 and 3 dimensions. It has a fractal dimension that reflects its complex branching structure. Similarly, the human circulatory system, with its branching veins and arteries, follows a fractal pattern, allowing it to fill the body efficiently while maximizing surface area. Fractal dimensions are not only beautiful in their connection to nature, but they also have practical applications. In physics, fractal geometry helps explain complex phenomena like the distribution of galaxies in the universe. The large-scale structure of the cosmos appears fractal-like in nature, with clusters of galaxies connected by vast voids, much like the intricate patterns we see in fractal mathematics. Understanding the fractal dimension of these cosmic structures allows scientists to make sense of the large-scale distribution of matter in the universe. Let's not forget about one of the most ubiquitous places where fractals appear: your computer screen. Many image compression algorithms, like those used in JPEGs, take advantage of fractal-like structures. These algorithms break down an image into self-similar patterns to compress the data. The idea is that images, especially natural scenes like forests or mountains, contain recurring patterns that can be represented efficiently using fractal mathematics. As a result, the fractal dimension of these patterns becomes crucial to understanding how computers can store and transmit images with minimal data loss. Fractal dimensions are also used in medicine, particularly in the analysis of complex structures like the brain. The brain's folding pattern, called gyrification, increases its surface area, allowing more neurons to fit in a confined space. This folded surface is fractal-like, with its intricate curves and folds repeating at different scales. Measuring the fractal dimension of the brain's surface can help neuroscientists understand the degree of folding and how it relates to cognitive abilities or disorders like schizophrenia. To visualize fractional dimensions, imagine inflating a balloon. At first, it looks like a simple two-dimensional circle. As it inflates, it becomes a three-dimensional sphere. But imagine if this process happened in stages, where each small increase in the balloon's size corresponded to adding some detail to its surface without fully turning it into a three-dimensional object. It would exist somewhere between 2 and 3 dimensions, much like how fractals and objects in nature can fill space in ways that defy our traditional understanding of geometry. In summary, fractional dimensions offer a powerful way to describe the complexity of the natural world. They break free from the limitations of whole number dimensions, allowing us to understand the intricate, self-similar patterns that appear in everything from coastlines to galaxies. Fractal dimensions give us the tools to describe shapes and systems that don't fit neatly into our usual categories, revealing the deep interconnectedness between mathematics and nature. While fractional dimensions may seem abstract at first, they provide a lens through which we can appreciate the subtle beauty and complexity of the universe around us. Spin networks. Spin networks are a profound concept in theoretical physics, particularly in the study of quantum gravity. They represent an attempt to describe the very fabric of the universe, space and time, using the principles of quantum mechanics. The idea of a spin network challenges the classical picture of space as a smooth, continuous expanse, and instead suggests that space may be made up of discrete units, interconnected like a vast web. Understanding spin networks is key to advancing our grasp of quantum gravity, the elusive theory that seeks to unify general relativity with quantum mechanics. To grasp the importance of spin networks, it's helpful to start with a simple analogy. Imagine a spider's web, intricately woven with threads that connect at specific points. Now, rather than thinking of these threads as mere fibers, imagine that they represent the very structure of space itself. The intersections, or nodes, in the web are points in space, and the threads between them represent relationships, or connections, between these points. But unlike an ordinary spider's web, the connections in a spin network aren't simple straight lines. They carry quantum information, like the spin of particles. Each thread has a value associated with it, representing a quantum property such as spin or angular momentum. The entire web is a mathematical representation of the geometry of space at the most fundamental level. The idea of a spin network was first introduced by physicist Roger Penrose in the 1970s. His goal was to build a quantum theory of space-time, something that general relativity, Einstein's theory, struggles to explain at very small scales. In general relativity, space-time is treated as a smooth, continuous fabric that can be stretched and warped by the presence of mass and energy. But when you zoom into extremely small scales, such as the Planck scale, about 10 circumflex 35 meters, the smoothness of space breaks down, and quantum effects become dominant. Penrose proposed that at these scales, space isn't smooth, but is composed of discrete building blocks, much like matter is composed of atoms. A spin network consists of nodes and links. The nodes represent quanta of space, and the links between them carry values of spin, hence the term spin network. These values are crucial because they describe how the nodes, or quanta of space, are related to one another. You can think of each node as a tiny grain of space, and the links as the glue holding them together. What's truly mind-bending is that according to spin networks, space itself emerges from these relationships. The geometry of space is not something that exists independently, but is the result of how these quanta are connected. One of the most exciting applications of spin networks is in the field of loop quantum gravity, a theory that seeks to quantize space-time. Loop quantum gravity builds on Einstein's general relativity but goes further by attempting to describe spacetime in a way that incorporates quantum mechanics. In loop quantum gravity, spin networks are used to model the structure of spacetime at the quantum level. Instead of thinking of space as a continuous fabric, loop quantum gravity suggests that space is woven from these tiny, discrete loops, with spin networks providing the mathematical framework for this structure. A key feature of spin networks is that they are not static. Just as the fabric of space can stretch and warp in general relativity, spin networks can evolve and change over time. The links between nodes can change, and the values of spin associated with these links can also change. This dynamism reflects the quantum nature of space-time, where nothing is fixed or absolute. The geometry of space is constantly fluctuating, even at the tiniest scales. One of the most profound implications of spin networks is that they suggest space and time are not fundamental properties of the universe, but are emergent phenomena. In classical physics, space and time are treated as a backdrop, an unchanging stage on which the drama of the universe plays out. But in the world of spin networks, space and time are seen as arising from deeper, more fundamental relationships. It's as if space and time are merely convenient illusions that emerge when you look at the universe on a large scale. But when you zoom into the smallest scales, they dissolve into a web of quantum interactions. This perspective has profound implications for our understanding of the universe. If space and time are emergent, then they might not exist in the same way at very high energies or in the extreme conditions near black holes or in the early universe. Spin networks give physicists a way to explore these extreme conditions and ask deep questions about the nature of reality. For instance, what happens to space and time at the moment of the Big Bang? Or inside a black hole where the gravitational pull is so intense that space and time are stretched to their limits. Spin networks offer a framework for addressing these mysteries by providing a quantum description of space-time. Another fascinating aspect of spin networks is their potential to unify the forces of nature. In the standard model of particle physics, forces like electromagnetism and the strong and weak nuclear forces are described by the exchange of particles, known as gauge bosons. Spin networks can be extended to include these forces, offering the tantalizing possibility of a unified theory that combines gravity with the other fundamental forces. This would bring us one step closer to a theory of everything, a goal that has eluded physicists for decades. In summary, spin networks offer a radical new way of thinking about space, time, and the fundamental structure of the universe. They represent a shift away from the classical view of space-time as smooth and continuous, toward a quantum view where space-time is discrete and emergent. Through the lens of spin networks, we see the universe as a dynamic web of quantum relationships, where the very geometry of space is shaped by the interactions of tiny, discrete units of space. This groundbreaking idea opens up new possibilities for understanding the deepest mysteries of the cosmos, from the nature of black holes to the origin of the universe itself. Emergent space-time. Emergent space-time is a profound concept that challenges the traditional understanding of space and time as fixed, fundamental properties of the universe. Instead, it suggests that space-time, as we perceive it, may not be fundamental at all. It might emerge from deeper, underlying principles that exist at the quantum level. This idea turns our everyday experience of the world upside down and opens up new ways of thinking about reality itself. To understand emergent space-time, let's dive into its roots and implications, using analogies and relatable concepts along the way. Imagine a hologram. At first glance, a hologram looks like a three-dimensional object with depth and volume. But if you take a closer look, you realize that the hologram is actually a two-dimensional surface. The three-dimensional appearance is just an illusion created by the arrangement of light on the surface. In a similar way, the idea of emergent space-time suggests that what we experience as three-dimensional space and one dimension of time might not be fundamental. It might emerge from a deeper reality, something that exists in a different form, just like the flat surface of a hologram. At its core, emergent space-time arises from the intersection of quantum mechanics and gravity. For decades, physicists have struggled to reconcile these two pillars of modern science. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity, Einstein's theory of gravity, describes how massive objects bend space-time. But when you try to apply both theories at the same time, say near a black hole or at the moment of the Big Bang, things break down. Equations yield infinities, and the fabric of space-time seems to tear apart. This is where the idea of emergent space-time comes into play. Instead of trying to force gravity and quantum mechanics to fit into the same framework, what if space-time itself emerges from quantum interactions? In this view, Spacetime is not the backdrop on which the universe plays out. It's a result of the universe's most fundamental processes. Just as a chair or table emerges from the arrangement of atoms, spacetime might emerge from the behavior of something more fundamental. One analogy for emergent spacetime is a block of ice. To our eyes, ice appears to be a solid, continuous object. But if you zoom in far enough, you'll see that the ice is made of individual water molecules, bound together by molecular forces. The solid structure of the ice is emergent. It arises from the interactions between those molecules. In a similar way, space-time might appear smooth and continuous on a large scale, but at the smallest scales, it could be made up of discrete elements such as quantum entanglements or other unknown entities. The solid structure of space-time that we experience might be the result of these fundamental interactions. One of the most intriguing ideas connected to emergent space-time is the holographic principle, proposed by physicist Gerard T. Hooft and developed by Leonard Susskind. The holographic principle suggests that all of the information contained within a volume of space can be described by information encoded on the boundary of that space. Think of it like a can of soup. According to the holographic principle, everything inside the can, the soup, could in theory be fully described by information on the surface of the can. In this sense, the three-dimensional reality we experience might be a kind of projection, an illusion generated by something happening on a lower dimensional boundary. This concept has been supported by research into black holes. When objects fall into a black hole, their information seems to be lost forever. At least, that's what classical general relativity would suggest. However, the holographic principle proposes that the information is not actually lost, but encoded on the event horizon of the black hole. This leads to the possibility that the entire universe could be described by information on its boundary in a lower dimensional form. In more recent years, researchers have explored the possibility that spacetime itself could emerge from quantum entanglement. Quantum entanglement is the strange phenomenon where two particles, once connected, remain correlated no matter how far apart they are. The state of one particle instantly affects the state of the other, even if they are separated by vast distances. Some physicists, like Mark van Ramsdonk, have proposed that spacetime could emerge from networks of quantum entanglement. The intricate connections between quantum particles could weave the very fabric of spacetime, much like threads in a tapestry. Imagine a patchwork quilt. Each individual square of the quilt is connected to its neighbors, and these connections form the larger fabric of the quilt. In a similar way, quantum entanglement could act like the threads that stitch together the fabric of spacetime. The more entanglement there is between particles, the more spacetime stretches and connects. This would mean that spacetime isn't something that exists on its own, but is the result of how particles are entangled with one another. The concept of emergent spacetime suggests that the deepest truths about the universe may lie not in the fabric of space and time itself, but in the underlying processes that give rise to them. We might one day discover that space-time, much like the hologram or the block of ice, is not as fundamental as we once thought. It could be a product of something far more profound, waiting to be uncovered by future generations of physicists. In conclusion, emergent space-time challenges the very way we think about reality. What we perceive as the continuous, smooth flow of space and time might, at its most fundamental level, be an emergent phenomenon arising from quantum interactions. This idea pushes the boundaries of our understanding and opens up new possibilities for how the universe works. It suggests that just as the universe emerged from a singularity in the Big Bang, space-time itself might emerge from the most fundamental interactions at the quantum level, the information universe. The universe we inhabit is filled with matter, energy, galaxies, and stars. But beneath all of these physical forms, an idea is gaining traction. What if the fundamental building blocks of the universe aren't particles or fields, but information itself? This concept, known as the information universe, challenges our deepest understanding of what reality is, suggesting that information, not matter or energy, may be the most fundamental entity in the cosmos. It's an idea that sounds abstract at first, but when unpacked, it touches on the very nature of existence, knowledge, and the fabric of space and time. To begin with, let's consider the nature of information. In its simplest form, information is a measure of uncertainty or knowledge about something. For example, if you flip a coin, the information is whether it lands on heads or tails. If you roll a die, the information is which number comes up. Information is the answer to a question, a resolution of ambiguity. Now, imagine that everything in the universe, from a single atom to an entire galaxy, can be reduced to a set of questions and answers, to a stream of bits like those in a computer. This is the crux of the information universe. This idea is most famously associated with physicist John Archibald Wheeler, who coined the phrase "it from bit." Wheeler suggested that everything in the universe, every physical it, whether a particle, a force, or even space-time itself, derives its existence from information or bit. This was a radical departure from the classical view of the universe as a machine governed by the interactions of particles and forces. In Wheeler's view, the universe operates more like a vast computational system, where reality is defined by binary decisions, much like how a computer operates on ones and zeros. To make this easier to grasp, consider a pixelated image. At first glance, the image looks like a smooth, continuous picture, but if you zoom in, you'll see that it's made up of individual pixels, each holding a bit of information, whether the pixel is on or off, black or white, and so on. The smooth picture emerges from the underlying bits of information, and if you alter the bits, you alter the image. In a similar way, what we perceive as the universe could emerge from the underlying information that defines every particle and every interaction. One of the most striking implications of this idea comes from black hole physics. Stephen Hawking's famous discovery, known as Hawking radiation, revealed that black holes are not entirely black. Over time, they slowly evaporate by emitting radiation. But this raises a troubling paradox. If a black hole eventually evaporates, what happens to the information about all the matter that fell into it? In the classical view of physics, information about the physical state of a system should never be lost. It's one of the foundational principles of physics. But in the case of black holes, it seemed that this information was being destroyed forever, leading to what's known as the black hole information paradox. This paradox prompted physicists to reconsider the role of information in the universe. If the information about matter falling into a black hole is not lost, then where does it go? One leading theory is that the information is encoded on the event horizon of the black hole, a thin shell surrounding it. This theory is connected to the holographic principle, which suggests that the entire three-dimensional universe could be thought of as information encoded on a two-dimensional boundary. Just as a hologram contains all the information needed to produce a three-dimensional image on a flat surface, the universe itself might be a projection of information stored on its boundaries. What's even more fascinating is that this view of the universe as information aligns with cutting-edge research in quantum mechanics. Quantum systems are governed by probabilities, and at the heart of quantum mechanics is the idea that information about a system is stored in its quantum state. But unlike classical information, which is either one thing or another, like a coin landing on heads or tails, quantum information can exist in superposition. This means it can be both heads and tails simultaneously, a state of ambiguity until it is observed. The concept of quantum entanglement further highlights the role of information in the universe. When two particles become entangled, their states are correlated in such a way that the state of one particle instantaneously determines the state of the other, no matter how far apart they are. This instantaneous transfer of information seems to defy the classical laws of physics, particularly the limit imposed by the speed of light. But if the universe is fundamentally made of information, an entanglement simply reflects how information is distributed and shared across space-time. Another important aspect of the information universe is the idea that the physical laws we observe may themselves be emergent from deeper informational processes. Just as a computer program runs based on lines of code, the universe may operate based on fundamental informational rules, ones we are only beginning to uncover. Some theorists propose that the laws of physics are not fixed but evolve over time, much like the flow of information in a complex system. This would suggest that reality itself is dynamic, constantly shaped by the processing and transformation of information. In essence, the information universe proposes a radical shift in perspective. Rather than seeing the universe as a static mechanical structure of particles and forces, it invites us to view reality as a dynamic, ever-evolving network of information. Whether it's the encoding of quantum states, the behavior of black holes, or the fundamental constants of physics, everything in the universe might ultimately be a product of information. Quantum Darwinism. Quantum Darwinism is a fascinating theory that takes its inspiration from natural selection, but it applies to the quantum world, a realm where particles can exist in multiple states at once and are governed by strange, often counterintuitive rules. To grasp quantum Darwinism, one has to first understand the peculiarities of quantum mechanics, particularly the way quantum systems behave when they are not observed. In the classical world, the world we experience every day, Objects have definite properties. A ball is either here or there. A coin is either heads or tails. But in the quantum world, particles can exist in a superposition, meaning they can be in multiple states at once. Imagine flipping a coin and having it land both heads and tails simultaneously. This is the strange reality of the quantum realm, where particles don't settle into a specific state until they are measured or observed. This phenomenon is known as the collapse of the wave function. The mystery deepens when we ask, what causes the collapse of the wave function? In other words, what forces a quantum system to choose a single outcome, such as a particle being in one position rather than another? Classical physics doesn't have this problem because objects are always in a definite state, but quantum mechanics leaves this up to chance, or so it seems. Enter quantum Darwinism, a theory proposed by physicist Wojciech Zurek in the early 2000s. Quantum Darwinism provides a possible explanation for why we see a classical world with definite outcomes. Even though the underlying nature of reality is quantum and probabilistic, the key idea here is that the environment plays a crucial role in determining what quantum information gets passed on to the macroscopic world, and which information gets selected out, much like Darwinian evolution selects for certain traits in a species. Let's imagine a quantum system, like an electron, that is in a superposition of multiple states. When this electron interacts with its environment, be it the surrounding air molecules, photons of light, or any other particles, it leaves traces of its state in the environment. But not all the information about the electron is passed on to observers like us. Instead, only certain robust properties of the electron get copied into the environment. This process is akin to natural selection in biology, where traits that offer a survival advantage get passed on to future generations, while others are weeded out. In the quantum world, only specific information about the system survives and becomes observable to the macroscopic world. To make this more relatable, consider a forest filled with trees. Each tree interacts with its environment, sunlight, wind, animals, and so on. But not every aspect of each tree becomes visible or relevant to a casual observer. The color of the leaves or the height of the tree might be obvious to you as you walk through the forest, but the microscopic details, such as the arrangement of individual cells in the leaves, remain hidden. In this analogy, the tree is the quantum system, and the environment is filtering out most of the irrelevant information, allowing only certain features, like leaf color and height, to become prominent to observers. Similarly, in the quantum world, the environment acts like a filter, amplifying certain robust properties of quantum systems, while the rest of the quantum information fades into irrelevance. This process leads to what we observe as classical reality. For instance, if you see an electron in a particular location, it's because the environment has selected that specific location from the many possibilities encoded in the quantum wave function. The rest of the possible locations, those that didn't make the cut, are effectively erased or hidden from our view. Quantum Darwinism helps to solve one of the central puzzles of quantum mechanics, the measurement problem, or why we don't see quantum superpositions in everyday life. According to this theory, the classical world we experience is just the tip of the quantum iceberg, shaped by the environment's selection of specific classical-like states from an underlying sea of quantum possibilities. This environmental selection acts as a sort of natural selection for information, determining which quantum states become part of our observable reality. But why is this important? It ties directly into the way we understand the transition from the quantum to the classical world. The problem of how the strange, fuzzy, and probabilistic nature of quantum mechanics gives rise to the solid, predictable world we live in has perplexed physicists for decades. Quantum Darwinism offers a solution by suggesting that the environment chooses for us. It explains why, despite the inherent uncertainty and superposition in quantum systems, we always seem to observe concrete, classical outcomes. To further clarify, imagine that every interaction a quantum system has with the environment is like sending out countless copies of a signal into the world. Those copies carry information about certain aspects of the system, just like how multiple people might witness an event and report the same details, reinforcing a single version of reality. The environment amplifies specific properties of quantum systems. As a result, many observers interacting with the same environment will report the same outcome. In this way, quantum Darwinism ensures that we all see a consistent, classical world. In summary, quantum Darwinism is a fascinating theory that draws parallels between biological evolution and the selection of quantum information. It explains how the classical world emerges from the quantum underpinnings of reality by positing that the environment plays a crucial role in selecting which aspects of quantum systems become observable. This idea not only offers a potential solution to the measurement problem in quantum mechanics, but also deepens our understanding of the nature of reality itself, suggesting that the universe is shaped by the flow and selection of information at a fundamental level. Supersolids. Imagine a material that flows like a liquid but also retains the structure of a solid. This might sound impossible at first, but it's the basic premise of a state of matter known as a supersolid. Supersolids are an extraordinary phase of matter where two opposing properties, fluidity and solidity, coexist in the same system, defying our traditional understanding of how matter behaves. To appreciate the strange nature of supersolids, we first need to recall what we mean by a solid and a liquid. A solid is defined by its ability to retain a definite shape with atoms or molecules locked into a rigid, structured lattice. A liquid, on the other hand, flows and takes the shape of its container because the particles within it can move freely. Normally, these two states are distinct and mutually exclusive. Something can be either a solid or a liquid, but not both. Now, imagine if a material could simultaneously possess the long-range order of a solid, where its particles form a structured lattice, but also flow without friction like a superfluid. This dual nature of a supersolid brings to mind an analogy of an ice sculpture that, while still maintaining its solid shape, can flow like water around obstacles without breaking apart. The particles inside the supersolid seem to experience a kind of quantum duality, behaving as though they are simultaneously in a fixed position and flowing freely. The journey to discovering supersolids began in the realm of superfluidity, which is itself a remarkable quantum state. Superfluids, discovered in helium at ultra-low temperatures, are fluids that flow without any resistance, meaning they can move endlessly without losing energy to friction. This is a direct result of quantum mechanics, where particles behave collectively in a coordinated wave-like manner, allowing them to bypass the classical limitations of friction. Supersolids extend the concept of superfluidity into the solid state. The possibility of a supersolid was first predicted in the 1960s, largely based on theoretical insights. Physicists speculated that if superfluidity could occur in a liquid, why not in a solid? The challenge was that no one had ever seen such a material, nor did they have a clear path to creating one. The breakthrough came in 2004 when researchers using helium-4, the same isotope used to discover superfluidity, found evidence suggesting that the helium-4 might exhibit supersolid behavior under extremely cold conditions. Helium-4 atoms, when cooled near absolute zero, can form a crystalline solid. However, under these extreme conditions, quantum effects dominate, and the atoms in the solid start to behave in a collective way, leading to a strange duality. Some of the atoms in the solid lattice appeared to flow without resistance, hinting at supersolid behavior. This discovery was both thrilling and puzzling. If these findings were correct, they meant that at incredibly low temperatures, the laws of classical physics, laws that rigidly separate solids and liquids, could be broken, and a new hybrid state of matter could emerge. However, it wasn't until later that researchers were able to replicate and refine these results, confirming the existence of supersolids in other materials beyond helium. The key to understanding supersolids lies in quantum mechanics. Unlike the behavior of everyday matter, where particles are localized in specific positions, quantum particles like those in helium-4 can exist in a delocalized state. In this state, the wave functions of the particles, mathematical descriptions of their quantum states, overlap and interfere, allowing the particles to act in unison. In a supersolid, some particles remain fixed in a lattice, maintaining the structure of a solid, while others are free to flow through the lattice, giving the material its fluid-like properties. Think of this in terms of a marching band. Normally, each musician would have a specific spot in a formation, representing a solid structure. But in a supersolid, some musicians can break free of their spots and move fluidly around the field, while the rest of the band remains in its original formation. Despite this fluidity, the overall shape of the formation is preserved, just as a supersolid can flow like a liquid while maintaining the structural order of a solid. One of the fascinating implications of supersolids is the potential insight they provide into quantum mechanics and many-bodied systems. Supersolids reveal how collective behavior can arise from individual quantum interactions, and they challenge our understanding of what is possible in the realm of condensed matter physics. They are a perfect example of how the counterintuitive world of quantum mechanics can manifest in strange and unexpected ways at macroscopic scales. But why should we care about supersolids? Beyond the sheer wonder of their existence, supersolids could provide valuable clues for developing new materials with exotic properties, possibly influencing future technologies. Their unusual combination of solidity and superfluidity could have applications in quantum computing or the development of frictionless materials, where energy losses are minimized due to the absence of resistance. Supersolids are still a very active area of research, with scientists continuing to explore their behavior and potential uses. Each new discovery in this field pushes the boundaries of our understanding of matter and highlights the versatility of quantum phenomena. As we explore the frontiers of quantum mechanics, supersolids stand as a testament to the fact that nature, at its most fundamental level, often behaves in ways that defy our classical intuitions. In conclusion, supersolids are one of the most mind-bending states of matter known to science, blending the characteristics of solids and superfluids in a way that challenges our conventional understanding of the physical world. They offer a glimpse into the strange and beautiful complexities of quantum mechanics, reminding us that the universe often operates under rules that are far more intricate and interconnected than we can easily comprehend. Quantum Zeno effect. The quantum Zeno effect is one of those deeply counterintuitive phenomena that seem to only exist in the strange and paradoxical world of quantum mechanics. To grasp its essence, let's start by thinking about an ancient paradox from which the effect gets its name, Zeno's paradoxes. Zeno of Elea, a Greek philosopher, posed a series of paradoxes about motion, one of which involves an arrow in flight. In this paradox, Zeno argues that if you were to take a snapshot of the arrow at any given moment in time, you would see it frozen, stationary in space. From this perspective, Zeno questioned how something that is motionless in every instant could ever move at all. Of course, in our everyday world, this idea seems absurd because we know arrows do indeed fly through the air. But in the quantum world, where the act of observation itself changes the outcome, Zeno's paradox takes on a bizarrely real form. The quantum Zeno effect suggests that the very act of observation can prevent a quantum system from evolving. To understand how this works, let's first recall one of the key features of quantum mechanics: superposition. In a superposition, a quantum particle, say an electron, can exist in multiple states simultaneously. For example, it can be in two places at once, or it can be spinning both clockwise and counterclockwise simultaneously. However, the moment we observe or measure this particle, the superposition collapses and the particle snaps into one definite state. Now, imagine you have a quantum system that is in a superposition, and you're waiting for it to evolve into a new state over time. Normally, if left alone, the system will eventually transition from one state to another. But here's where things get interesting. According to the quantum Zeno effect, if you continually observe the system in rapid succession, you can prevent this transition from happening. The system will remain frozen in its initial state, just like Zeno's arrow that seems to never move. The analogy for this effect in the everyday world is like repeatedly peeking at a boiling pot of water. Imagine you're heating water, waiting for it to boil. Every time you lift the lid to check, the water stops heating, and it never reaches a boil. In the quantum realm, this constant observation essentially freezes the state of the system, inhibiting its natural evolution. This was first proposed in 1977 by physicists Baidyanath Misra and George Sudarshan, who theorized that continuous observation could halt the decay of an unstable particle. And indeed, the quantum Zeno effect has since been experimentally observed in various quantum systems, providing yet another piece of evidence for the deeply strange nature of the quantum world. To dive deeper, let's consider an experiment that showcases the quantum Zeno effect in action. Take an unstable particle, like an excited atom that is supposed to emit a photon and decay to a lower energy state over time. Normally, this atom will eventually release its energy in the form of a photon and drop to a stable state. However, if you continually measure whether the atom is still in its excited state, the act of measurement will interfere with the atom's ability to decay. In fact, with frequent enough measurements, you can prevent the atom from emitting its photon and decaying altogether, effectively freezing it in place. This seems counterintuitive because we are used to thinking of time as an unstoppable force, something that relentlessly pushes systems forward from order to disorder, from birth to decay. However, in quantum mechanics, the flow of time can be altered by observation. The more you observe, the less things change. But why does this happen? The answer lies in the fact that quantum measurements disturb the system being observed. Every time you measure a quantum system, you're resetting its wave function, the mathematical object that describes its superposition of states. Frequent measurements prevent the system from having enough time to evolve naturally. In other words, the act of measurement continually collapses the system back to its initial state before it has the chance to transition to a new one. It's as if you're watching a DVD of a movie, and every time you press the play button, the movie starts from the beginning again. The more often you press play, the less progress the movie makes. While the quantum Zeno effect might seem like an exotic theoretical oddity, it has real-world applications and implications, particularly in the field of quantum computing. Quantum computers rely on maintaining superpositions for as long as possible to perform calculations. The quantum Zeno effect can be used to stabilize qubits, the basic units of quantum information, by preventing them from prematurely transitioning to unwanted states, thus helping to preserve the integrity of the computation. Furthermore, the effect has deep implications for our understanding of time, reality, and the nature of observation. It forces us to rethink what it means to observe something, suggesting that the mere act of looking at a system fundamentally alters its behavior. In this sense, the quantum Zeno effect isn't just a curiosity of the quantum world. It's a powerful demonstration of the active role that observers play in shaping the very reality they're trying to measure. In conclusion, the quantum Zeno effect exemplifies the profoundly strange and interconnected nature of quantum mechanics. It challenges our everyday intuitions about time, change, and observation, revealing a universe where reality itself can be shaped by the act of watching. Whether preventing an atom from decaying or keeping a quantum system in a stable state, the quantum Zeno effect highlights just how fundamentally different the quantum world is from the one we experience in our everyday lives. Negative mass. The concept of negative mass sounds like a bizarre contradiction to everything we know about the physical world. Mass in our everyday experience is a measure of how much matter an object contains, and it's always positive. If you pick up a rock, it resists being moved. This is inertia, the tendency of mass to resist changes in motion. But what if, instead of resisting motion, an object accelerated in the opposite direction of the force applied to it? This is where negative mass comes into play, and it's not just a theoretical curiosity. It opens up some truly strange implications about the universe. To understand the idea of negative mass, let's start by thinking about how mass works in the familiar world of Newtonian physics. In classical mechanics, Newton's second law tells us that force equals mass times acceleration, FMR. If you apply a force to an object with positive mass, the object will accelerate in the direction of the force. Push a car, and it moves forward. Now imagine what would happen if the mass were negative. Instead of accelerating in the direction of the force, it would move in the opposite direction. Push a car with negative mass, and it would accelerate backward. This idea seems completely alien to our everyday experiences. Objects with positive mass have inertia. They resist being pushed. Negative mass, by contrast, would seem to behave almost like an anti-object. It would have anti-inertia, accelerating away from whatever force you applied to it. If you tried to push such an object forward, it would paradoxically move backward. The mind-bending implications don't stop there. Consider Newton's law of gravitation, which states that any two objects with mass attract each other. This is why the Earth orbits the Sun, and why objects fall to the ground. But with negative mass, gravity behaves in unexpected ways. If an object with positive mass and an object with negative mass are placed near each other, they would repel one another. The object with positive mass would experience a normal gravitational attraction toward the negative mass, while the negative mass would experience a gravitational repulsion from the positive mass. This means that the two objects could, in theory, chase each other around forever. The positive mass would be drawn toward the negative mass, but the negative mass would repel and accelerate away, creating a bizarre perpetual motion system. Now, you might wonder if such an object could actually exist. As strange as it seems, negative mass isn't forbidden by the laws of physics. In fact, certain theoretical models in general relativity and quantum field theory allow for the possibility of negative mass under specific conditions. One of the key areas where negative mass might come into play is in exotic forms of matter like dark energy, or in the concept of wormholes, hypothetical shortcuts through spacetime. Wormholes, which are solutions to Einstein's equations, would need something to keep them from collapsing. Negative mass could provide this exotic matter to hold open a wormhole and allow travel between distant parts of the universe. But have we ever observed negative mass in the real world? While no clear-cut evidence for negative mass exists, researchers have conducted experiments that simulate its effects under controlled conditions. In 2017, physicists at Washington State University created a fluid using ultra-cold rubidium atoms that behaves as though it has negative mass. When they pushed the atoms, the fluid accelerated in the opposite direction, mimicking the bizarre behavior expected from negative mass. Though these experiments don't involve true negative mass, more a simulation or an analog, they do give us insight into how systems with negative mass might behave. Negative mass, if it exists, could provide answers to some of the biggest mysteries in modern physics, including the nature of dark energy and the expansion of the universe. Dark energy, which makes up about 68% of the universe, is responsible for the accelerating expansion of space. Some theorists speculate that negative mass could play a role in dark energy's effects. If negative mass were scattered throughout the cosmos, its repulsive gravitational effects might drive galaxies apart, explaining the ever-increasing rate at which the universe is expanding. This ties the idea of negative mass to the very structure of spacetime, linking it to our understanding of the universe's ultimate fate. Despite its allure, the concept of negative mass remains highly speculative. It hasn't been observed in nature, and the mathematical models that describe it often come with complications that make it difficult to incorporate into mainstream physics. For example, negative mass tends to violate certain principles of thermodynamics, like the conservation of energy under classical physics. However, in the quantum realm, where particles and fields often behave in ways that defy our classical intuitions, the door remains open for negative mass to play a role. Another potential area of investigation lies in Hawking radiation, the theoretical process by which black holes slowly evaporate. Stephen Hawking proposed that pairs of virtual particles, one with positive mass, the other with negative, could form near the event horizon of a black hole. In this scenario, the negative mass particle would fall into the black hole, reducing its total mass, while the positive mass particle would escape, carrying energy away. This process could provide a clue as to how negative mass might manifest in the extreme environments of black holes. In summary, while negative mass is not something we encounter in our everyday lives, it offers a fascinating glimpse into how the universe might work at its most extreme and fundamental levels. Whether it's helping us understand the expansion of the cosmos, keeping wormholes stable, or playing a role in black hole physics, negative mass is a concept that stretches the boundaries of our current understanding. It challenges our intuitions, forcing us to think beyond the familiar laws of motion and gravity, and opens the door to new possibilities in both theoretical and experimental physics. As we continue to explore these frontiers, negative mass may one day offer answers to some of the universe's deepest mysteries. Vacuum decay. Imagine the universe as a vast landscape of hills and valleys, with each valley representing a possible state of reality. Now, envision that the universe is currently resting in a particular valley, a state of balance we call the false vacuum. While this may sound stable, there's an unsettling possibility lurking beneath the surface. We may not be in the true lowest energy state, but rather a precarious temporary one. And if that's the case, the very fabric of reality could change in an instant, in a process known as vacuum decay. At the heart of vacuum decay is the idea that the vacuum of space, far from being truly empty, has energy associated with it. This energy defines the vacuum's state and, in turn, the fundamental forces and particles that make up the universe. The false vacuum refers to the possibility that the universe exists in a local minimum of energy, like a ball resting in a shallow valley on the landscape, rather than the absolute minimum, or true vacuum. The true vacuum, in contrast, would represent a more stable, lower energy state. The unsettling question is, what happens if the ball rolls out of its shallow valley into the deeper, true vacuum? The transition from a false vacuum to a true vacuum is what scientists refer to as vacuum decay. If this transition occurs, it would have catastrophic consequences for the entire universe. A bubble of true vacuum could spontaneously form somewhere in the universe, perhaps due to quantum tunneling, a process that allows particles or even vacuums to transition to different states without needing the energy to cross an energy barrier. This bubble would expand at nearly the speed of light, obliterating everything in its path. The fundamental laws of physics as we know them would change, making life, stars, planets, and even atoms incompatible with the new reality. But why haven't we seen any signs of vacuum decay? Why are we still here, living in this precarious false vacuum? To understand this, we need to delve into the nature of energy landscapes in quantum field theory. In the standard model of particle physics, fields like the Higgs field define the vacuum state of the universe. The Higgs boson, discovered in 2012, is responsible for giving particles mass, and its properties are tied directly to the vacuum energy. If the energy of the Higgs field is not at its absolute minimum, the universe could be vulnerable to vacuum decay. Fortunately, calculations suggest that even if the universe is in a false vacuum, the decay process is extremely rare and might not happen for trillions of years. The lifetime of the universe in its current state could vastly exceed the current age of the universe. Still, it's not a comforting thought. Vacuum decay could happen at any time without warning, and there would be no way to detect or predict it in advance. The bubble of true vacuum would travel faster than light, meaning we would never see it coming. One analogy to grasp this abstract concept is to think about supercooled water. Water typically freezes at 0 degrees Celsius, but in certain conditions, it can remain liquid below this temperature in a state called supercooling. This supercooled liquid is stable until a disturbance, a dust particle or a sudden motion, causes it to crystallize into ice. The process of vacuum decay is similar. The universe could be like supercooled water appearing stable while being poised for a catastrophic transition to a more stable state. But is vacuum decay just a mathematical curiosity, or is there real cause for concern? This depends largely on the exact nature of the Higgs boson and the values of certain constants in the Standard Model. If the mass of the Higgs boson lies within a certain range, it suggests that the universe is metastable, meaning it's in a false vacuum, but could eventually decay. As of now, the precise values of these constants are still under investigation, and we cannot definitively say whether vacuum decay is a remote theoretical possibility or a more imminent risk. One of the profound implications of vacuum decay is that it highlights just how finely tuned our universe is. The delicate balance between the forces of nature, the masses of particles, and the energy of the vacuum all point to an extraordinary degree of precision. This raises deep questions about the nature of the universe. Why is the universe so seemingly fine-tuned to allow life to exist? Does this fine-tuning suggest the existence of multiple universes, each with different vacuum states? In some of those universes, vacuum decay may have already occurred, and the entire cosmos could have been reshaped by this invisible cataclysmic process. The idea of vacuum decay, while terrifying, also provides insight into the profound mystery of existence itself. It reminds us that reality is not just a passive stage for the drama of the universe, but an active participant with its own hidden dynamics and dangers. While vacuum decay remains an abstract concept, it forces us to confront the fragility of everything we take for granted. In a universe governed by quantum mechanics, the vacuum is far from empty or passive. It's a dynamic, seething entity with the potential for drastic change. And while vacuum decay may be an improbable event far in the distant future, it serves as a humbling reminder that the universe is far stranger and potentially more dangerous than we can fully comprehend. Godel's universe. In 1949, Kurt Godel, the famous logician known for his incompleteness theorems, did something remarkable. He ventured into the realm of cosmology. Partnering with his friend Albert Einstein, Godel sought to explore the possibilities of time and space in the context of Einstein's general theory of relativity. The result of this intellectual journey was one of the most mind-bending ideas in the history of physics, Godel's universe, a solution to Einstein's field equations that allowed for something previously thought impossible, closed time-like curves, or in simpler terms, time loops. Imagine for a moment that you live in a universe where time is not a straight line stretching from past to future, but a loop, where the past, present, and future wrap around on themselves. In this universe, if you set off on a journey in the right direction, you could theoretically travel far enough to end up back at the moment you started. Godel's universe suggests just that, a universe where time is not linear, cyclical, raising the profound possibility of time travel and questioning our most basic assumptions about the nature of time itself. Godel's discovery came as part of his work with Einstein's theory of general relativity, which describes how matter and energy distort space and time. These distortions create the phenomenon we call gravity. Godel took Einstein's equations and looked for a solution where the universe was rotating. This was not a hypothetical tweak for the sake of curiosity. Godel genuinely believed that the universe could possess this kind of rotation. In this rotating universe, the fabric of space-time behaves in an extraordinary way. Time ceases to be absolute and can curve back on itself. To understand this better, let's use an analogy. Picture the Earth as a rotating sphere. If you travel along its surface, you can go around the globe and eventually return to your starting point. Now replace the Earth with the entire universe, and instead of traveling across a physical surface, imagine moving through time itself. Just as you would come full circle on Earth, Godel's universe allows you to come full circle in time. The timeline of events you experience could potentially bring you back to a point in your own past. The implications of this are staggering. If time can loop, then cause and effect, the fundamental relationship that underpins our understanding of reality, becomes ambiguous. Events could occur without a clear beginning or end. If you travel to your past, you might even be able to influence events that have already happened. This opens the door to paradoxes that defy common sense, like the famous grandfather paradox, where you could theoretically travel back in time and prevent your own birth. Godel's universe also poses deep philosophical questions about the nature of free will. In a universe where time loops, the concept of a predetermined fate becomes inescapable. If time is cyclical, does that mean everything is destined to repeat itself? Are our choices merely illusions, with our lives following a preordained script that plays out over and over again in the loops of time? Though Godel's solution was mathematically sound, it posed serious challenges to the physical interpretation of the universe. Observational evidence shows that the real universe is not rotating as Godel's solution suggests. The cosmos, as far as we can tell, is expanding but not rotating in a way that would allow for these closed time-like curves. However, Godel's universe remains an important theoretical construct because it demonstrates that, within the framework of general relativity, time is not as rigid as we tend to believe. The concept of Godel's rotating universe brings us face to face with the idea that time may be more flexible than the simple ticking of a clock. Einstein had already revolutionized our understanding by showing that time could stretch and contract depending on the relative speed of observers and the presence of strong gravitational fields. Godel pushed this even further, suggesting that time itself could bend back upon itself in ways that are difficult to even visualize. What Godel's universe ultimately demonstrates is that our understanding of time, though intuitive and useful in daily life, may be fundamentally flawed at a cosmic scale. The idea that time could loop challenges our perception of progress, history, and the very nature of reality. It also highlights the limitations of human understanding when faced with the vast and often counterintuitive laws that govern the universe. Though Godel's universe remains a theoretical curiosity, it has inspired generations of physicists and philosophers to rethink the nature of time. It also serves as a testament to Godel's brilliance, showing that his genius extended far beyond the realms of logic and mathematics into the mysteries of the cosmos. In the end, Godel's universe may not describe the reality we inhabit, but it stands as a powerful reminder that the true nature of time might be far stranger than anything we have yet imagined. In a universe as vast and mysterious as ours, time, like space, might not always behave in the ways we expect. Time might not just flow, it might loop, twist and bend in ways that we are only beginning to comprehend. Conformal cyclic cosmology. The universe, as vast and mysterious as it is, has long been thought to follow a narrative of birth, expansion, and eventual death. But what if this story of the cosmos doesn't have a single beginning or end? What if the universe we know is just one chapter in an infinite book of cosmic cycles where each end is merely the beginning of another? This is the intriguing premise of conformal cyclic cosmology, CCC, a theory proposed by renowned mathematical physicist Sir Roger Penrose. To understand CCC, let's start with a familiar image, the life cycle of a phoenix. In mythology, the phoenix is a bird that dies in a burst of flames, only to be reborn from its ashes. In much the same way, Penrose's theory suggests that our universe goes through cycles of death and rebirth. After it reaches its end, it doesn't remain in a final state of entropy or heat death, but instead transitions into a new Big Bang, creating a fresh universe with new matter, energy, and life. And this has been happening infinitely, long before the Big Bang that started our own cosmos. Penrose's theory draws on Einstein's general theory of relativity, which describes how space-time is warped by mass and energy. However, the novelty of CCC lies in its approach to the end state of the universe. According to most mainstream cosmological models, the universe will keep expanding forever, gradually cooling down as stars burn out and galaxies drift apart. Eventually, in what's called the heat death, the universe will reach a state of maximum entropy where all energy is evenly distributed, and nothing more can happen. The stars will go dark, and the universe will enter an eternal, lifeless void. But Penrose challenges this view. He argues that as the universe expands, its geometry begins to stretch out, becoming more uniform. Eventually, in the distant future, this stretching causes the distinctions between time and space to blur. When all matter decays, there are no longer any clocks ticking or distances to measure, and in this future, time itself loses meaning. At this point, the end of the universe becomes conformal. In other words, its shape mirrors the conditions of the universe's birth. The result? The end of one universe resembles the state before the Big Bang so closely that it seamlessly transitions into the beginning of a new universe. To grasp CCC, it's essential to understand the terms conformal and cyclic. In physics, conformal geometry refers to shapes or structures that preserve angles but not necessarily sizes. Imagine inflating a balloon covered with a grid of squares. As the balloon expands, the squares stretch, but their internal angles remain the same. Over time, the balloon could stretch so much that it looks flat. Penrose's theory suggests something similar happens to the universe. As it expands over trillions of years, distances become meaningless, but the universe's overall shape remains. Meanwhile, cyclic refers to the idea that the universe doesn't have a single start and finish, but instead passes through repeating cycles. After each end, the universe is reborn, with time resetting itself to begin a new eon. In Penrose's vision, this cycle of death and rebirth has no ultimate beginning or end, just an endless series of big bangs and expanding universes. Penrose and his colleagues have even claimed to find evidence for CCC in the cosmic microwave background, that's CMB, the faint afterglow of the Big Bang that still pervades the universe today. This radiation is often thought of as the oldest light in the cosmos, revealing information about its early moments. What Penrose has proposed is that concentric circles found in the CMB could be ripples from violent events that occurred in a previous universe, such as supermassive black holes colliding. These rings, according to CC, are imprints of ancient cosmic activity from before the Big Bang, possibly providing glimpses into the eon that preceded ours. Though these findings remain highly speculative, they add weight to the possibility that our universe is part of a much grander cycle. What makes conformal cyclic cosmology so radical is the way it challenges our understanding of the universe's history. In most models, the Big Bang is treated as an absolute beginning, a moment of creation from which time, space, and matter emerged. But CCC reframes this idea, suggesting the Big Bang is simply a phase transition in an endless cycle of cosmic births and deaths. For the average person, thinking about CCC can feel overwhelming. Our everyday experience of time, linear with clear beginnings and endings, seems incompatible with the notion of infinite cycles. But Penrose's theory, while abstract, offers a new way to think about the nature of existence. Rather than a single universe destined for eventual decay, CCC gives us a picture of a cosmos that is endlessly regenerative. In this model, we may be living in the latest cycle of a universe that has existed for untold eons before us. And when our universe reaches its conclusion, it will give rise to another, a universe that will carry the faint echoes of our own existence, imprinted in the fabric of space-time, like ancient footprints in the sand. Conformal cyclic cosmology may never be proven, but it challenges us to think about the universe in new and profound ways. It dares us to imagine a cosmos without a final end, where the arrow of time bends back upon itself, creating a loop that stretches across infinite eons, with no beginning or end in sight. Entropic gravity. Gravity, for centuries, has been one of the most mysterious forces in the universe. From Newton's apple falling to Einstein's warping of space-time, our understanding of gravity has evolved in groundbreaking ways. However, an even more radical and less conventional theory has entered the conversation in recent years. Entropic gravity, proposed by Dutch theoretical physicist Erik Verlinde in 2010. Entropic gravity posits that gravity might not be a fundamental force at all, but rather an emergent property of entropy. In other words, gravity could be the result of the universe's tendency toward disorder, making it less of an intrinsic force and more of a side effect of information distribution in space-time. To grasp the profound implications of this theory, it helps to break it down into digestible ideas, analogies, and concepts. This isn't just about the pull between the Earth and the Moon. It's a view of gravity that could change how we understand the very structure of reality. The term emergent is central to understanding entropic gravity. In science, an emergent phenomenon is something that arises from the collective behavior of many smaller parts, rather than existing as a fundamental building block. For example, temperature is an emergent property of molecules in motion. No single molecule has temperature, but when trillions of them move, the collective motion can be described as heat. Verlinde's entropic gravity suggests something similar about gravity itself. Instead of being a fundamental force like electromagnetism, it could emerge from the underlying principles of thermodynamics, particularly entropy. Entropy is the universe's relentless march toward disorder. It's a fundamental concept in thermodynamics that describes the number of microscopic configurations a system can take. Imagine a library filled with neatly arranged books. If you were to randomly shuffle those books, there are far more ways to create a disordered library than there are to restore the pristine, ordered arrangement. This tendency toward disorder is entropy. Now let's apply this concept to the structure of space-time. According to Berlin, when particles in spacetime are in an area of low entropy, forces like gravity emerge naturally as spacetime attempts to balance itself. This is akin to how water flows downhill to balance its own level. Gravity, then, is not a force pulling objects together. Rather, it's the result of spacetime seeking a higher state of entropy, of spreading out and balancing the underlying information. One way to picture this is to think of gravity like the tension you feel when pulling on a rubber band. The more you stretch it, the more it resists. Similarly, Verland posits that as objects move apart in spacetime, they create a form of tension in the universe's information field, and this tension is what we interpret as gravity. The universe, like the rubber band, seeks to return to a state of lower tension, or maximum entropy. The force we experience as gravity is simply spacetime's response to this informational imbalance. To understand this on a cosmic scale, consider how massive objects like the Earth or the Sun curb spacetime in Einstein's theory of general relativity. Berlin's theory suggests that this curving is not a fundamental interaction, but an emergent property, a byproduct of how spacetime organizes itself. Central to entropic gravity is the idea that information is a physical entity. This may sound abstract, but information theory, developed by Claude Shannon in the mid-20th century, showed that information is not just about communication or data, but is fundamentally tied to physical systems. In Berlin's view, the microscopic details of particles and fields contain information, and how this information is distributed affects the large-scale behavior of spacetime. When we think of spacetime as a kind of information matrix, gravity can be viewed as an emergent effect arising from how information is processed and organized. As spacetime evolves toward maximum entropy, towards spreading out the information, this drive creates the force we call gravity. The holographic principle, a concept originating from black hole physics, also plays a crucial role in Verlinde's idea. The holographic principle suggests that all the information contained within a volume of space can be described by information on the boundaries surrounding that space, much like a hologram encodes three-dimensional information on a two-dimensional surface. Verlinde's entropic gravity ties into this principle by suggesting that gravity arises from the information stored on the surfaces of objects, rather than within their volumes. Imagine a planet surrounded by an invisible information screen or surface. As objects near this surface, their movement and behavior are influenced not by the planet's mass itself, but by the information encoded on the surface. In this framework, gravity is not a fundamental interaction, but an emergent property, reflecting the organization of this information. The implications of entropic gravity are profound, not only because it provides an alternative to Einstein's theory of general relativity, but also because it could offer new insights into mysteries such as dark matter. According to Berlin, if gravity is an emergent phenomenon tied to information and entropy, then the discrepancies we see in galaxies, where gravity seems stronger than expected, leading to the dark matter hypothesis, could be explained as an effect of the information structure of spacetime, rather than requiring the existence of unseen dark matter. While still highly speculative and controversial, entropic gravity offers a new lens through which to view the cosmos. It invites us to consider gravity not as a fundamental aspect of the universe, but as a secondary effect, an echo of spacetime's deeper information processes. This would not only shift how we understand gravity, but also how we comprehend the nature of spacetime and the fabric of reality itself. Berlin's entropic gravity is still in its infancy, and many questions remain unanswered. But it stands as a bold challenge to long-held assumptions, asking us to rethink one of the most basic forces in the universe as a product of entropy, the universe's constant march toward disorder, mirror matter. Imagine looking into a mirror and seeing a perfect reflection of yourself, a world identical to the one you live in, but flipped, where left is right and right is left. Now stretch this analogy to the fabric of reality itself. What if the universe had a counterpart, a mirror image, where the particles, forces, and matter are similar but obey an opposite symmetry? This idea forms the foundation of mirror matter, a theoretical concept, suggesting that our universe might have a hidden twin, an invisible realm made up of mirror particles. The notion of mirror matter stems from a larger idea in physics: symmetry. Physicists have long been captivated by the symmetries that seem to govern the universe, from the symmetrical shapes in nature to the symmetrical laws of physics. But sometimes symmetry is broken or incomplete. In fact, one of the most mysterious asymmetries we observe is the imbalance between matter and antimatter. Mirror matter is one possible explanation for how the universe retains overall symmetry while appearing asymmetric in specific ways. To understand mirror matter, we must first explore the importance of symmetry in physics. Symmetry is more than just a pleasing aesthetic. It's a fundamental principle in the laws of nature. For example, the equations that describe electromagnetism are symmetrical, meaning they behave the same, no matter which direction they're applied. But in the case of certain processes, such as the weak nuclear force, which governs radioactive decay, this symmetry is broken. The discovery of parity violation in 1956 showed that the universe does not always respect left-right symmetry in these processes. However, this left-right asymmetry raised a puzzle. If the universe breaks symmetry in certain areas, how can the total system still maintain balance? One possible answer lies in mirror matter. The hypothesis is that there is a mirrored version of all known particles, but they interact through their own set of mirror forces. This would allow the universe to obey symmetry at a fundamental level while still explaining the observed violations in our familiar world. Mirror matter, if it exists, would be made of particles that are identical to those found in regular matter, but they would obey mirror symmetry. In this hypothetical mirror world, every particle we know, electrons, protons, and neutrons, has a corresponding mirror particle. These mirror particles would interact with each other just like regular matter interacts in our universe, but with one major caveat. Mirror particles would interact very weakly, if at all, with regular matter. This weak interaction is key to why we haven't yet detected mirror matter. Since mirror particles only interact with regular matter through gravity or other extremely weak forces, they would be effectively invisible to us. This makes them an intriguing candidate for dark matter, the mysterious, unseen substance that makes up approximately 85% of the matter in the universe. If mirror matter exists, it could be the missing link that explains why galaxies rotate the way they do, despite not having enough visible mass to account for their motion. At first glance, the idea of mirror matter might sound like science fiction, but it arises from well-established principles in particle physics. Parity violation, discovered in the 1950s by Qian-Xiong Wu's famous experiment, revealed that certain particles, such as neutrinos, only spin in one direction, left-handed. This discovery was a shock because until that point, physicists believed that the laws of physics were the same whether applied to a left-handed or right-handed system. Mirror matter restores this lost symmetry by postulating that for every left-handed particle, there is a right-handed mirror version. In this way, the universe as a whole retains symmetry, even if our observable part appears asymmetric. But this symmetry goes deeper than just particle physics. The very forces that govern interactions, like electromagnetism and the strong nuclear force, could also have mirror counterparts. Mirror photons, mirror gluons, and even mirror gravity could exist, shaping a parallel universe that operates under the same fundamental laws, but remains completely invisible to us, except through gravitational effects. One of the most compelling reasons to take the mirror matter hypothesis seriously is its potential to solve the mystery of dark matter. Dark matter is inferred from its gravitational effects on galaxies and galaxy clusters, but it does not emit or interact with light in any way that we can detect. Mirror matter offers a neat solution. If galaxies contain large amounts of mirror matter, this invisible mass could account for the gravitational anomalies that have puzzled scientists for decades. The mirror universe could be just as full of stars, planets, and galaxies as our own, but these celestial bodies would be made of mirror atoms, and their light would interact with mirror photons, not the regular photons we see. In this scenario, dark matter halos surrounding galaxies could actually be mirror galaxies composed entirely of mirror matter, quietly shaping the evolution of the universe while remaining hidden from our direct detection. As intriguing as mirror matter may be, finding direct evidence for its existence is extraordinarily difficult. Since mirror particles interact so weakly with regular matter, traditional methods of detection, such as particle colliders or telescopes, aren't effective. However, some researchers have proposed looking for subtle gravitational anomalies or rare interactions between mirror matter and regular matter as a potential avenue for discovery. There are also theoretical challenges. For instance, if mirror matter exists, why is there such a vast imbalance between regular matter and its mirror counterpart? The answer to this question may lie in the very early universe, where symmetry-breaking events could have caused mirror matter to remain largely invisible, while regular matter became dominant in our observable universe. While mirror matter remains a speculative idea, it's a compelling one that touches on some of the deepest mysteries in modern physics. It offers a way to restore symmetry to the universe, while also providing a potential explanation for dark matter. Whether or not we ever discover the elusive mirror universe, the idea of mirror matter challenges us to rethink our assumptions about the cosmos and reminds us that the universe may be far more complex and far more symmetrical than we ever imagined. Relational quantum mechanics. In our everyday world, it's easy to think of objects as existing independently from one another. A tree stands tall whether or not you're looking at it, and a rock remains firmly in place even when no one observes it. But in the quantum world, things aren't quite so straightforward. The peculiar nature of quantum mechanics suggests that reality is not something fixed and absolute. It shifts and bends depending on what is observing it or interacting with it. This is the essence of relational quantum mechanics, RQM, a unique interpretation that suggests the properties of quantum objects only exist in relation to other objects, rather than being independent features of the world. To understand what makes relational quantum mechanics so intriguing, let's first revisit the core dilemma of quantum physics. Quantum mechanics famously challenges our classical intuitive notions of reality. Take, for example, Schrödinger's cat, a thought experiment that illustrates the bizarre state of superposition. In this scenario, a cat is placed in a box with a device that may or may not kill it, depending on a random quantum event. Until the box is opened and an observer checks on the cat is both alive and dead, existing in a limbo of possibilities. But the question is, why should it take an observer to determine the state of the cat? Is the act of measurement or observation really what makes reality solidify from possibilities into a single outcome? In traditional interpretations of quantum mechanics, this has been a challenging idea to grapple with. Some interpretations suggest that consciousness or measurement collapses a quantum system from superposition to a definite state, while others insist that many possible realities branch out into parallel universes. As in the many worlds interpretation, relational quantum mechanics proposes a different perspective altogether. It asks us to reconsider what we mean by reality itself. In relational quantum mechanics, the key idea is that quantum systems don't have absolute intrinsic properties. Instead, these properties only make sense in relation to another system. This means that a quantum particle doesn't have a definitive position, spin, or energy until it interacts with another particle or observer. Think of it like a conversation. Imagine you and a friend are discussing a book. Your opinions about the book are shaped by your interaction with each other. You may find yourself agreeing on some points or diverging on others. The insights that emerge from the conversation are not properties that either of you owned beforehand. They come into existence through the interaction itself. Similarly, in RQM, quantum properties are like opinions. They arise only through the interaction between systems, and they can differ depending on who is involved in the conversation. Let's break it down with a more concrete analogy. Imagine a quantum coin existing in a superposition of heads and tails. If you, as an observer, measure the coin, it will randomly settle into one of these two states, heads or tails. But according to relational quantum mechanics, this outcome isn't absolute. It is only heads in relation to you. For another observer who hasn't yet seen your measurement, the coin is still in a state of superposition, both heads and tails. This idea suggests that reality is deeply observer-dependent. But here's the twist. Observers themselves are also quantum systems. So while you may measure the coin as heads, to a third system like a distant quantum detector, you, the coin, and your measurement are all part of a larger quantum relationship. The result you obtain, heads, isn't an absolute fact about the universe. It's simply one piece of information within a larger web of relationships. Relational quantum mechanics challenges the classical view that objects have definite properties independent of observation or interaction. In the relational view, there is no God's eye view of reality, where a universal observer knows the definitive state of every particle. Instead, every quantum system is embedded in a network of relationships, and its properties only exist in relation to other systems. In other words, the universe doesn't have a single unchanging state. Instead, it's filled with countless perspectives. Each quantum system interacts with others, creating different versions of reality depending on the relationships between them. These realities don't contradict one another. They're simply different facets of the same underlying web of interactions. Relational quantum mechanics also suggests that reality is a kind of information exchange. When two quantum systems interact, they communicate information to one another, establishing the properties that will be observed. This is a departure from the more classical notion of a deterministic clockwork universe, where every particle has a set trajectory and position. Think of reality as a massive, interconnected web. At each point in the web are quantum systems like beads on a string. These beads don't have independent existence. They only have meaning through their connections to other beads. And these connections are constantly shifting as systems interact and exchange information. This perspective aligns with a broader philosophical shift in physics, where information is increasingly seen as a fundamental building block of the universe. Instead of thinking of particles and forces as the ultimate, quantum gravity, when we think about the universe, space seems like a static stage, a vast arena where events unfold. But what if space itself is not a smooth, continuous fabric, but something more granular, more discrete, and intriguingly, emergent from simpler building blocks? This idea forms the basis of a fascinating theoretical framework called quantum gravity, a concept that seeks to explain the emergence of space-time itself. Before diving into quantum gravity, it's important to grasp the mystery physicists are trying to solve. Einstein's general theory of relativity tells us that space-time is not a passive backdrop. It's a dynamic entity capable of bending and stretching in response to mass and energy. Gravity, in this sense, is nothing more than the curvature of space-time. Yet, general relativity treats space-time as a continuous entity, much like a smooth fabric. On the other hand, quantum mechanics, which governs the behavior of particles at the smallest scales, describes the universe in terms of discrete quantities, quanta. This clash between the continuous and the discrete presents a fundamental problem in modern physics. How can these two pictures of reality, one describing smooth space-time and the other describing granular quantum particles, coexist? Quantum gravity offers a potential solution to this conundrum by suggesting that space-time itself might not be fundamental. Instead, it could emerge from an underlying network or graph of more basic entities, much like how solid matter emerges from the arrangement of atoms. Just as the properties of a crystal arise from the specific arrangement of atoms, the properties of space-time could emerge from a network of quantum relationships. To visualize this, imagine a graph, a set of points called nodes, connected by lines called edges. Each node represents a fundamental element, and the edges between them represent interactions or relationships. Initially, this graph is in a highly disordered state, like a chaotic tangle of strings with no clear structure. But over time, as the universe cools from its hot, early state, the graph undergoes a phase transition, a transformation from disorder to order. As it does, the connections between nodes rearrange themselves, giving rise to something resembling space-time. This concept of a phase transition is central to quantum gravity. In much the same way that water can change from a liquid to a solid when it freezes, the underlying quantum graph can undergo a transition that transforms it from a chaotic structureless form into something that looks like smooth space-time. In the early universe, during the first moments after the Big Bang, the graph might have been in a hot phase where connections between nodes were constantly changing, and space-time didn't exist as we know it. But as the universe expanded and cooled, the graph could have frozen into a more ordered phase, where nodes became locked into a particular structure, giving rise to the familiar geometry of space-time we experience today. This idea is revolutionary because it suggests that space-time isn't a pre-existing entity. It's something that emerges as a result of quantum processes. To make this more relatable, imagine a digital photograph. At first glance, the picture appears to be a continuous image, with no clear divisions between one part and another. But when you zoom in far enough, you'll discover that the image is actually composed of individual pixels, discrete units, that together create the illusion of a continuous picture. Quantum gravity suggests that space-time could work in a similar way. At large scales, space-time appears smooth and continuous, like the photograph. But if you zoom in far enough, down to the Planck scale, the smallest possible size in the universe, you might find that space is made up of discrete units, like the pixels in the photo. These units could be the nodes and edges of the quantum graph. This analogy helps us understand how something seemingly continuous and smooth, like space-time, can emerge from something fundamentally discrete and granular. One of the most exciting aspects of quantum gravity is its potential to offer a new way to think about gravity and general relativity. Gravity is the curvature of space-time. But if space-time itself is emergent from a quantum graph, then gravity might emerge from the way these nodes and edges interact. In other words, gravity could be a result of the collective behavior of the underlying graph, rather than a fundamental force in its own right. This could provide crucial insights into one of the biggest challenges in modern physics, reconciling general relativity with quantum mechanics. By viewing space-time as emergent, quantum gravity offers a bridge between the continuous world of gravity and the discrete world of quantum particles. Although quantum gravity remains a speculative theory, there are ways to potentially test its predictions. If space-time truly emerges from a quantum graph, there might be observable signatures of this process, particularly in the early universe. For instance, scientists could look for traces of this phase transition in the cosmic microwave background radiation, the afterglow of the Big Bang, or in the distribution of galaxies across vast cosmic distances. Furthermore, the theory suggests that at incredibly small scales, space-time should exhibit a kind of granularity, much like the pixels in a photo. Advanced experiments, perhaps using gravitational waves or other precision measurements, might be able to detect these tiny structures, offering indirect evidence for the quantum nature of space-time. Quantum graphity represents a bold step into the unknown, challenging our deepest assumptions about the nature of space, time, and reality itself. By suggesting that space-time emerges from a network of quantum relationships, it offers a radical new way of thinking about the universe, a universe that is not built on a static foundation, but one that is constantly evolving and reshaping itself at the most fundamental level. If proven correct, it could revolutionize our understanding of the cosmos, opening up new frontiers in both quantum physics and cosmology. Superfluid vacuum theory. Imagine for a moment the vacuum of space, the vast emptiness that exists between planets, stars, and galaxies. Most of us are taught to think of this vacuum as precisely that, empty, a void devoid of matter, energy, or anything of substance. But what if this nothingness wasn't empty at all? What if instead it behaved more like a strange and exotic fluid, constantly in motion, underpinning the entire universe? This radical idea is at the heart of superfluid vacuum theory, SVT. To understand superfluid vacuum theory, we first need to challenge the idea of what a vacuum is. In classical physics, a vacuum is simply the absence of matter, a space where particles don't exist. However, in quantum physics, the vacuum is much more complicated. The quantum vacuum is alive with activity. Virtual particles constantly appear and disappear. Energy fluctuates in and out of existence, and the nothingness is in fact seething with quantum activity. Superfluid vacuum theory takes this a step further by proposing that the vacuum itself is a superfluid, a state of matter that behaves in extraordinary ways. A superfluid is a substance that flows without friction. You can think of it as a fluid that once in motion never slows down or stops, no matter what it encounters. Superfluids also have quantum properties that allow them to behave in ways that seem to defy classical physics. To make this idea more tangible, let's take an example from the laboratory. Scientists have observed superfluidity in certain materials like liquid helium. When helium is cooled to a temperature near absolute zero, it enters a superfluid state where it can flow up the sides of containers and through tiny pores without any resistance. It can create vortices that last indefinitely and move in ways that are completely alien to our everyday experiences with fluids like water. Superfluidity in the lab, though fascinating, pales in comparison to the mind-bending possibility that the vacuum of space itself could be a superfluid. If the vacuum behaves like a superfluid, it could provide an entirely new framework for understanding the fabric of reality. One of the driving motivations behind SVT is the quest for a unified theory of physics, something that can reconcile the two giants of modern science: Einstein's general theory of relativity, which governs the large-scale structure of the universe, and quantum mechanics, which explains the behavior of particles at the smallest scales. General relativity treats space as a continuous fabric that bends and warps in response to mass and energy. Quantum mechanics, on the other hand, describes the universe in terms of particles and probabilities, with no clear sense of space as a fluid-like medium. Superfluid vacuum theory offers a potential way to merge these two views by suggesting that space-time itself emerges from a deeper, fluid-like medium. In this theory, space-time isn't a passive backdrop. It's a dynamic, superfluid vacuum. The equations of general relativity might emerge as an effective description of how this superfluid behaves on large scales, while the weirdness of quantum mechanics could be a manifestation of how particles interact with this fluid on very small scale. To make this concept easier to understand, imagine fish swimming in a river. To the fish, the river feels like an unchanging environment. They swim through it without necessarily being aware of the water's flow. But the river is not static. It's a dynamic system with currents, eddies, and turbulence. The fish, in their limited perspective, don't realize that their movement is influenced by the river's flow. In the same way, we humans experience space-time as a static, unchanging entity. We live our lives, interact with particles, and observe gravity without being aware of the deeper fluid-like medium, the superfluid vacuum, that governs all of this. The behavior of particles, forces, and even spacetime itself might be the result of how they interact with this quantum superfluid. One of the most intriguing aspects of superfluid vacuum theory is the idea that elementary particles, such as electrons, quarks, and photons, could be vortices or disturbances in this superfluid vacuum. Just as whirlpools form in a river, particles might be localized, stable vortices in the superfluid of spacetime. This concept is revolutionary because it shifts the focus away from particles as fundamental building blocks, and instead views them as excitations of the vacuum itself. These vortices would be stable configurations of the superfluid vacuum, and their properties, mass, charge, spin, would arise from how they interact with the surrounding fluid. In this sense, particles aren't individual objects floating through space. They're disturbances or twists in the fabric of the vacuum. This viewpoint echoes other ideas in theoretical physics, such as string theory, where particles are not point-like objects but are instead vibrations of a more fundamental entity. If superfluid vacuum theory is correct, it could have profound implications for our understanding of the universe. For one, it might provide insights into the nature of dark energy and dark matter, two mysterious components that make up most of the universe but remain poorly understood. These phenomena could be manifestations of the superfluid vacuum's behavior on cosmic scales. Additionally, SVT could help explain some of the paradoxes and inconsistencies in current physics, such as the incompatibility between quantum mechanics and general relativity. By viewing space-time as a superfluid, we might find a way to bridge the gap between these two frameworks, providing a more unified picture of reality. However, superfluid vacuum theory is still in its infancy. While it offers a tantalizing vision of the universe, much work remains to be done to develop the mathematics behind the theory and to test its predictions through experiments and observations. Superfluid vacuum theory challenges our most basic assumptions about space, time, and matter. By proposing that the vacuum of space behaves like a superfluid, it offers a new lens through which to view the universe, one where particles are not independent objects but ripples in a vast quantum fluid. This theory, if proven correct, could transform our understanding of the cosmos, unveiling a new medium that underlies the very fabric of reality, the amplituhedron. In the world of quantum physics, particles interact with each other in a dizzying array of possibilities. Every time two particles collide, they can scatter in countless directions, producing a cascade of new particles. To predict the outcomes of these interactions, physicists use Feynman diagrams, intricate webs of lines and loops, representing all the possible particle interactions. The more complex the interaction, the more tangled the diagram becomes, and calculating the probabilities from these diagrams can become a monstrous task. But what if there were a way to bypass this complexity entirely? Enter the amplituhedron, an elegant, geometric object that promises to simplify quantum interactions in a revolutionary way. Let's start with the problem the amplituhedron seeks to solve. In quantum field theory, the framework used to describe particle interactions, particles don't just follow simple paths from point A to point B. Instead, they take every possible path simultaneously. These interactions are calculated using Feynman diagrams, a tool introduced by physicist Richard Feynman in the 1940s. The diagrams break down each possible interaction into a series of steps, or vertices, where particles meet and exchange energy. But as more particles get involved, the diagrams explode in complexity. For example, in a simple two-particle scattering, the calculation might be manageable, but as you add more particles and energy exchanges, the number of diagrams grows exponentially. Calculating the probabilities for these interactions, called scattering amplitudes, becomes a painstaking process that could require hundreds or even thousands of diagrams. The amplituhedron offers a radical new approach, cutting through this complexity by eliminating the need for most of these diagrams. Rather than computing each interaction step by step, it encodes the entire process in a single, elegant geometric structure. The amplituhedron was discovered by Nima Akani Hamed and his colleagues in 2013, and it upended the traditional ways physicists approached quantum field theory. Instead of thinking about particles interacting in space-time, the amplituhedron organizes these interactions in a way that doesn't require the concept of space-time at all. This is a profound shift in how we think about the fundamental nature of the universe. Imagine particle interactions as a complex dance. Each dancer, particle, has a role, and together they move in intricate patterns. Traditionally, physicists would track each dancer's movement frame by frame, recording every twist, turn, and exchange in great detail. But the amplituhedron allows physicists to take a step back and look at the dance as a whole. Rather than analyzing each movement individually, the entire dance can be represented as a single, cohesive shape. This shape, the amplituhedron lives in a mathematical space far removed from our familiar world of dimensions. It's not an object that exists in space or time, but a higher dimensional geometric form that encodes the scattering amplitudes of particles directly. In this way, it removes much of the redundancy present in Feynman diagrams, revealing a simpler underlying structure that governs particle interactions. The real power of the amplituhedron lies in its ability to simplify the mind-boggling complexity of quantum interactions. Traditional methods rely on space-time as a backdrop for all calculations, but as quantum field theory has evolved, it's become clear that space-time itself might be an emergent property, something that arises from deeper, more fundamental principles. The amplituhedron sidesteps space-time entirely, offering a new way of thinking about the quantum world where these dimensions aren't fundamental but secondary. For example, when particles scatter at high energies, the number of possible interactions grows exponentially. In traditional approaches, calculating the probabilities for such events could involve thousands or even millions of Feynman diagrams. Each diagram represents a small piece of the interaction, and putting them together to get the final result is a laborious process. However, the amplituhedron consolidates all of this into a single, elegant structure, dramatically simplifying the calculations. To give a sense of how powerful this is, consider a basic quantum interaction involving gluons, the particles that mediate the strong force inside atomic nuclei. Using conventional Feynman diagrams, calculating the scattering amplitude for just 8 gluons would require tens of thousands of diagrams. But with the amplituhedron, this calculation can be reduced to a single geometric formula, a staggering simplification. At its core, the amplituhedron is a reminder that the universe may be governed by beauty and simplicity at its most fundamental level. It suggests that the tangled web of particle interactions we observe in nature may be the result of an underlying order, a geometric harmony that we are only beginning to understand. The discovery of the amplituhedron also raises profound questions about the nature of reality. If we can describe particle interactions without referring to space-time, does this mean space-time itself is an illusion, a byproduct of a deeper, more abstract, mathematical reality? Could the universe itself be nothing more than the unfolding of geometric relationships, where particles are merely reflections of a hidden, higher dimensional structure? While the amplituhedron has already yielded incredible insights, it is still a developing area of research. Physicists are exploring whether this geometric approach can be extended to other forces and particles in nature, potentially leading to new breakthroughs in quantum field theory, and perhaps even offering clues to the long-sought theory of everything. The implications are vast. If the amplituhedron can describe the interactions of fundamental particles so elegantly, it might help bridge the gap between quantum mechanics and general relativity, two theories that currently resist unification. The simplicity it offers could provide a new way to view the universe's fundamental working, one where geometry rather than space, time, or energy is the true building block of reality. The amplituhedron is not just a mathematical curiosity. It represents a new way of thinking about the universe. By stripping away the complexities of Feynman diagrams and providing a direct link to scattering amplitudes, this geometric object offers a glimpse into a simpler, more profound layer of reality. It's a bold reminder that beneath the apparent chaos of quantum interactions, there may lie an elegant, geometric order waiting to be uncovered. MOND, a radical approach to dark matter. In the vast expanse of the cosmos, there are mysteries that continue to baffle scientists. One of the biggest puzzles is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, yet appears to make up about 85% of the universe's mass. Since the 1970s, astrophysicists have been trying to explain why galaxies behave the way they do, why their outer stars move at speeds that defy the gravitational pull calculated using visible matter alone. The standard explanation is that an invisible, exotic form of matter called dark matter fills the universe, providing the necessary extra gravity. But what if dark matter isn't needed to explain these cosmic anomalies? Enter modified Newtonian dynamics, or MOND. This controversial theory proposes that we don't need dark matter to explain the strange behavior of galaxies. Instead, we might need to change how we understand gravity itself, the puzzle of galactic rotation curves. To understand why MOND was proposed, we need to look at galactic rotation curves, the speed at which stars orbit the center of galaxies. According to Newton's law of gravitation, stars farther from the galactic center should orbit more slowly than those closer in, much like planets in our solar system. In our solar system, Mercury orbits the Sun much faster than Neptune because it's much closer to the Sun and feels a stronger gravitational pull. However, when astronomers began measuring the speeds of stars in galaxies, they discovered something unexpected. The stars in the outer regions of galaxies were moving much faster than they should be based on the amount of visible matter in the galaxy. According to Newtonian gravity, they should have been flung out of the galaxy like a stone spun too fast in a slingshot. But they weren't. They were still orbiting steadily. This led scientists to believe that some unseen mass, dark matter, must be providing the extra gravitational pull necessary to hold these fast-moving stars in place. A new idea, modifying gravity. In 1983, Israeli physicist Mordechai Milgram proposed an alternative explanation. Maybe Newton's laws of gravity don't work the same way on cosmic scales as they do on Earth. His idea, MOND, suggests that at very low accelerations, such as those experienced by stars at the outer edges of galaxies, the force of gravity behaves differently than expected. In other words, gravity might not weaken as quickly as Newton's law suggests when you get far enough from the center of a galaxy. Instead of requiring the existence of invisible dark matter, MOND modifies Newton's second law, F-ma, force equals mass times acceleration, by introducing a new parameter that adjusts how gravity works at low accelerations. In this framework, the gravitational pull felt by stars in the outskirts of galaxies would be stronger than predicted by Newton's laws, which would explain why those stars aren't flung out of their galaxies. A simple solution. MOND has a certain appeal because it can predict galactic rotation curves without needing to invoke dark matter. With just a small modification to the laws of gravity, it explains the observed behavior of stars in galaxies. No need for unseen particles or exotic physics. MOND has been especially successful in predicting the rotation curves of many types of galaxies, including those with very little visible matter, where dark matter models sometimes struggle. Imagine you're trying to explain how a car speeds down a racetrack. The standard model of physics, dark matter theory, suggests that the car has an invisible booster attached, giving it extra speed. MOND, however, argues that you don't need the booster at all. Instead, the car's engine might just work differently than you thought at certain speeds. The car speeds up naturally under the right conditions, without needing any mysterious external force. Challenges and criticisms. While MOND has its successes, it faces significant challenges. The most obvious criticism is that it doesn't explain the full range of cosmic phenomena. MOND works well on the scale of individual galaxies, but it struggles when applied to galaxy clusters, where dark matter models seem to hold up better. Galaxy clusters are groups of galaxies bound together by gravity, and their dynamics suggest even more missing mass than individual galaxies. MOND alone doesn't account for the additional gravitational pull observed in these clusters. Moreover, MOND doesn't fit easily into the broader framework of modern physics. Dark matter fits well with general relativity and the lambda-cold dark matter model, LCDM, which describes the universe on large scales. In contrast, MOND's modifications to gravity don't easily mesh with general relativity, which is a cornerstone of modern cosmology. Furthermore, the discovery of the cosmic microwave background radiation, the afterglow of the Big Bang, supports the dark matter model. The ripples in this radiation suggest that some invisible form of mass, likely dark matter, must have existed in the early universe to help form galaxies. MOND, as it stands, doesn't naturally explain these observations. The ongoing debate. MOND remains a controversial but compelling idea. Despite its challenges, it has sparked important conversations about the nature of gravity and the limits of our understanding. Its success in explaining galactic rotation curves with such simplicity forces physicists to question whether dark matter is the only solution to these mysteries. Even if MOND isn't the final answer, it's possible that it points to a deeper truth about gravity and the universe. Some physicists have explored hybrid models that combine aspects of MOND with dark matter, suggesting that both could play a role in explaining the cosmos. Others are investigating whether MOND could be connected to a deeper theory of quantum gravity, something that could eventually unify quantum mechanics with general relativity. Conclusion: a provocative alternative. The modified Newtonian dynamics theory offers a provocative alternative to the dark matter paradigm. By tweaking our understanding of gravity at low accelerations, MOND challenges the dominant cosmological models and forces us to reconsider the fundamental forces that shape our universe. Whether or not MOND is ultimately proven correct, its contributions to the field demonstrate the importance of questioning established ideas and exploring new ways of thinking about the cosmos.